Okay, so today I'm going to be presenting on a paper we've recently published in Environmental Research Letters entitled Multiscale Mapping of Plant Functional Groups and Plant Traits using Field Spectroscopy, UAV Imagery, and Sentinel-2 data. So first of all, why are we interested in studying vegetation in the high Arctic? Well, as I know this has already been covered quite a lot during this conference, I won't spend too long on it, but changing vegetation patterns in the Arctic have very large knock-on effects for the Earth's climate in terms of albedo. So the advancing vegetation line northwards reduces the albedo in the Arctic, as well as graminoids and grasses being replaced by shrubs also reduces albedo in the Arctic. Permafrost dynamics, so vegetation can influence the permafrost beneath it in various ways. Carbon cycling, so increased productivity in the Arctic can draw down more carbon and lock it into plants. But of course, changing vegetation dynamics can also change the permafrost, releasing carbon and methane into the Earth's atmosphere. And lastly, at a more local level, changing vegetation dynamics in the Arctic has a knock-on effect on food webs and on the species that depend on certain vegetation species in their diets. So this is why we're interested in studying vegetation. Secondly, how do we study vegetation in the Arctic? Well, of course, I'm sure you're all used to seeing these chambers dotted around the Arctic landscape. So a traditional way of measuring vegetation and studying it is in these enclosed chambers. Now, this provides very detailed information about the plants you can find within these chambers, the species, the plant traits, etc., and how they change. But a limitation to this method is a difficulty of knowing if the information that we obtain from these chambers is representative of the larger landscape. And if we see changes of vegetation within these chambers, how do we attribute that on such a small scale? How can we say the exact abiotic and maybe biotic drivers that are driving these vegetation patterns and changes at a landscape scale? And then of course, at the other end of the spectrum, we have satellite maps and satellite analyses. So this is the Kavan map, which is created using Landsat data of about 30 meters by 30 meters. And this is very good at studying the Arctic at a sort of pan-Arctic scale. But again, it's not so useful at a more local landscape scale. There isn't so much nuance within these individual parcels of vegetation. So it's difficult to capture small-scale vegetation dynamics and really see what's happening at a more local landscape scale. So the aim of this study was threefold. First of all, to try and predict species identity and plant traits using field spectroscopy, so 400 to 2,500 nanometers. Which I'll talk about a bit more in a minute. Secondly, to try and predict species identity and the same plant traits using drone spectra. And this is multispectral drone spectra of 5 bands. And thirdly, to explore methods of upscaling the drone data to the wider landscape using Sentinel-2 imagery. So, first of all, a quick background to spectral remote sensing from a vegetation perspective. So first of all, the sun shines on the Earth's surface. Some of that light is absorbed by vegetation for photosynthesis, but some of that light is reflected. And that reflected light can be captured by sensors mounted on a drone or on a satellite, for example. And this is an example of the reflected light of vegetation spectra ranging from 400 to 2,500 nanometers. And some of that light is in the visible spectrum. So this is light that our eyes can see. But a lot of that captured light is in the infrared spectrum, which is light that our eyes can't see, but it contains a kind of treasure trove of ecological information. So by analysing the bumps and wiggles in this vegetation spectra, we can derive information about the vegetation below. So we can derive chemical and biochemical information. For example, in the visible spectrum here, we can derive information about chlorophyll and about nitrogen concentration. And these dips up here in the infrared part of the spectrum correlate to moisture levels, so we can see how moist a plant is or how water stressed it is, for example. And by sort of combining all of this chemical information, we hope that maybe species have unique chemical fingerprints. So we can combine all this information to hopefully derive species information about the plants below. So that's how spectral remote sensing works. And using field spectroscopy, we can derive these really nice continuous vegetation curves, as I was saying, from about 400 to 2,500 nanometers. But using this multispectral drone camera, which you can see here, which is the exact one that we flew in Svalbard, this only measures information at 5 points across the spectrum. So instead of having 2,100 numbers with which to derive information, we only have 5 numbers. So we have the blue band, the green band, the red band, and then 2 bands in the infrared part of the spectrum at the red edge and at the near infrared. So one of the questions is, what can we derive with this perfect field spectroscopy information? And then what can we derive if we downscale to only using these 5 bands on the drone? So here is some information about our study sites. We had 3 study sites, all located within easy reach of Longyearbyen here. We collected information at the bird cliffs, just around at Bjørndalen, information at the control gradient, just above Isdamen, and here at the ITEX site in Endalen. And we were in Svalbard as part of Plant Functional Trait Course 4. So this is a course which goes around the world, and every 2 years it takes vegetation and trait information in different places around the world. So it's in previous years, it's been in Peru and in China, and I think they have a next course planned in Chile. So this is a course which is trying to collect global plant trait information to try and answer some global questions about changing vegetation patterns. But this year it took place on Svalbard, and we were the drone group, as you can see here. So there were lots of groups focusing on different aspects of vegetation, and the aspect we were focusing on was trying to upscale this field data and these sort of field level analyses to a wider landscape level. And this is the method that we used. So first of all, we flew a drone, a solo drone equipped with the 5-band Megasense camera that you saw earlier over a site. So this is the bird cliffs. This is the ford, and then this is the bird cliffs up here. And this is a nutrient gradient. So of course you have all of the organic matter from the bird cliffs that are being inputted into the vegetation up here, and that nutrient gradient is decreasing from the bottom of the bird cliffs here down to sea level. So first of all, we flew the drone and collected this nice map. And secondly, we took vegetation information. So across the site, we extracted 94 turfs. You can see the turfs here. They measured about 20 centimeters by 20 centimeters. And we took species ID, trait information, and also this field spectroscopy data. And we also took some extra species information as well. And all of these points were GPS'd with a very high spec differential GPS. Here are the results of the field spectroscopy. So we have the 3 different plant groups here. We have mosses, graminoids, and shrubs. And you can see that there are some quite clear differences between these spectral curves which gives us confidence that we can distinguish between these different plant groups. And then here at the species level as well, we can see, especially with the mosses and the graminoids, we have some quite clear spectral differences between the different species, which also gives us confidence that we can distinguish between these different species later on. Interestingly, there was a little, maybe a little bit less difference between the shrubs in their spectral curves here. We performed a cluster analysis with these spectral curves, and you can see here that all the mosses are pretty much clustered together up here. We also had some very tight clustering of salix and some of Lutzilla as well, whereas Dariusz and Cassiope were a bit more confused in their clustering. We then performed random forest. So this is a machine learning algorithm which takes these spectral curves and it calibrates itself on about 70% of the spectral information, and then uses the last 30% and tries to predict the remaining 30% of the vegetation data. So here are its predictions for all of the different species we collected. And you can see that there were some very high predictions for the three mosses. We've got 85%, 80% and 80% accuracy. Overall, we had a total accuracy of 74%. This was reduced slightly, as you could see in the previous cluster analysis, with the Cassiope and the Dariusz spectral curves being quite confused between each other. And with this sort of perfect species or perfect spectral information, we used the full spectral information, but then we also cut it just to the 5 bands. We replicated the drone information. But even with the replicated drone information, we were still predicting species at about 66% accuracy. And then with plant traits, we did the same thing. We use 70% of the spectral information to calibrate our machine learning models, and then use those calibrated models to predict the unseen 30% of the plant trait information. And we got R-squared values ranging from 0.88 for predicting water content, 0.77 for nitrogen, and then a bit lower for phosphorus and for our C-N ratios. And again, when we replicated the mecosense information, this dropped a bit for the water, which is unsurprising as water is expressed across, in many bands across the whole spectra, whereas nitrogen is mainly represented in the visible part of the spectrum. So actually cutting out a lot of the infrared here didn't make much difference, as we might expect. And then scaling up to the drone, we were actually unable to predict species information when we were using the actual drone. And this is probably due to a few things. Even though with our replicated drone information, we had a species accuracy of 66%, when using the actual drone information, we had an absolute accuracy of much lower. And this is probably due to some illumination difficulties when flying the drone. Of course, it's quite difficult in the Arctic where you have quite cloudy conditions, spectral mixing as well, and a very heterogeneous tundra where we needed very, very precise coordinates, because even if we were, 10 centimeters out, what we were saying was one species of moss might actually have been a completely different species of moss. And even though we had a very, very accurate GPS, we still had errors of about 10 centimeters, which for some of our samples may have been an issue. So we may have been saying that, this was grass when in fact it was moss, just because we were 10 centimeters out. But we were able to create a map of plant functional group. So a map of mosses, graminoids, and dwarf shrubs, as you can see here, with a total accuracy of about 72%. So this is still interesting. And we can see that we have graminoids where we have the wettest areas of this site. So here at the confluence between two drainage channels, we have a high graminoid percentage here. And mosses were found sort of around the edge of these alluvial fans, so in the rockier rockier area where maybe some other vegetation found harder to colonize. And again, here's some trait information for the bird cliffs. So we have very moist vegetation here where the graminoids are in these wet areas. And then actually, as you can see, we have this drainage channel coming down here. And at the outlet of this drainage channel, we often had very high nitrogen and phosphorus values. So clearly this drainage channel is bringing all of these nutrients that are coming off the bird cliffs, and they're flowing down this drainage channel and then being outputted at the bottom here and picked up by the vegetation. So we have some nice patterns from our drone information that seem to be matching up fairly well with what we were seeing at the site and what we would expect given the kind of micro topography at the site. And then scaling up to the Sentinel level, we use two methods here to try and upscale our water. So first of all, we took our water map, and this is our UAV created water map, and we resampled it to the resolution of Sentinel imagery. And we just used these Sentinel pixels to calibrate and validate exactly the same kind of model that we'd been using for the drone data. But this meant that we were calibrating and validating the Sentinel data directly. And then secondly, we just applied our drone model directly to the 5 Sentinel bands that match the drone bands most closely. So in method A, we're accounting for the fact that maybe Sentinel has slightly different, a different sort of quality of imagery compared to our drone imagery. Maybe it's a bit darker, you've got a bit more atmosphere in the way. So we're accounting for those differences. Whereas with method B, we're literally just taking our drone model, which has been calibrated on drone imagery, and just applying it to Sentinel data. And here are the results. As we can see, in method B, we have values which are looking quite unrealistic. So we know they're about sort of 80 to 100% water content, which probably isn't correct. And method A is demonstrating some much more realistic water values. So we would probably recommend using method A compared to method B. So calibrating and validating the Sentinel data directly. Unfortunately, with these two maps, we don't really have any data that we can use to validate these maps themselves. So we're not presenting them as potentially completely accurate. We're more trying to demonstrate the difference between these two different methods, so that when we had more drone data and more ground truth data to calibrate and validate these maps, that we could be producing in the future at a more accurate level. So I think that's pretty much my time up. So any questions?
Okay, thank you. And thank you for the presentation. The Cryosphere Virtual Laboratory is a ESA project, and it's 5 partners: NORCE, Norwegian Met Office, the Nansen Center, Science and Technology, and the Norwegian Polar Institute that develops this project. CVL is all about open science. So we try to put together a lot of data relevant for the cryosphere, like in situ data, model data, and Earth observation data that is already available in most cases on the internet, but we try to combine them and make tools to make them easier accessible, and the software for easier processing, visualization, and data discovery. We are working on predefined workflows for accessing the data and processing them. And we provide a generic platform to support scientific work in many interdisciplinary contexts. So this is just an example of what you would like to do to, for instance, to combine data from the CIS services, synoptic data, and climate data time series, all together in the map. So, and this is what we want to do. So the data sets we're using have to follow the FAIR principle. They should be findable, accessible, interoperable, and reusable. And this is, of course, SIOS is has also adopted this principle. So CVL will find data in various data. Going by itself. Find data from various sources, collect them, and then the users can utilize the tools we are providing. So we have implemented or are in the process of implementing these different workflows, and in the when the laboratory is fully functional, the users can implement their own, for instance, Jupyter notebooks and run them on their own computer or on virtual machines. So the workflows, here is an example of a workflow where users go to the landing page, choose type of processing, list of Jupyter notebooks, and then they can access a virtual machine and create a local machine. And for instance, and this can, for instance, be accessed through various possible interfaces. So in the GitHub of CVL, we will put hopefully a lot of these examples, so other users can be inspired by building upon the use cases that already are available. We have also implemented an advanced visualization tool that where you can look at the data in 3 dimensions. So here is an example using Sentinel-2 data for snow cover mapping. And it's also important to know that the visualization tool can be embedded in the Jupyter notebooks that the users are using. So here is an example where we can look at the snow cover fraction in Svalbard for a period in June, July. And let me see, I don't want to run the whole movie. This is in June, July. And if I go here, we have also done the same using MODIS. So you can see that the spatial resolution of MODIS is much coarser than Sentinel-2, but the bigger details are similar. We can also compare single days, like this. This is snow cover from Advental on 18th of June 2018 using Sentinel-2 and MODIS. So there are similarities and differences. And we are also using it for many other purposes. Here's an example over Greenland, where we received the albedo as a time series from the GEOS in Denmark. So the Jupyter notebooks we're developing, it's becoming a very common way of providing processing tools. In the project, we're developing 5 different use cases where we want to show how to do this quite scientifically, but also we hope that the users of CVL will develop their own notebooks where they can provide many different interesting showcases for Cryosphere research. And in particular, if you want to or you need to process a lot of data, we have also been coupled with the ESA's Polar Thematic Exploitation Platform, PTEP. And using PTEP will allow the CDL users to have virtual machines where they can run their Jupyter notebooks. This is the link to the PTEP. At the current time, we're soon going to open a call where early adopters can apply for funding. So we will we'll provide 20 grants for 3,000 euros each, where typically master or PhD students can apply for a grant, and then they are obliged to implement a Jupyter script that is run on the CVL infrastructure. And at the end, we hope that they can share the scripts with the rest of the community. So this was rather short, but CVL is an ESA project that will provide access to ICT tools and data for easier access, processing, and visualization of Cryosphere data. Thank you.
So thanks again for the introduction, and I prepared a talk on tidewater glaciers on the eastern coast of Svalbard, and I was interested in the surface elevation dynamics and the retreat rate of the glaciers, and I was trying to use some old archival data that are available. So first of all, I would like to say a few words about my motivation for that, because unlike the others, I'm not really a remote sensing expert, but as the fieldwork last year and also this year was more or less cancelled, so I was searching for some other work that should be used for my primary research site and the fieldwork. And I was also searching for some available data for a project that is starting this autumn on the development of the coastal systems. And I found a very nice digital elevation model, which inspired me for this work. And apparently no one has used it, as far as I know. So basically the aims of the study or the small project is to assess the tidewater glacier dynamics in terms of the retreat rate and surface elevation changes. And I also wanted to see if there are some common spatial patterns among the glaciers studied, and if we can somehow generalize the findings. So the study site is the coast of Svalbard, actually this southern part, very close to Hornsund, very famous location where a lot of studies have been done. And the study site is actually limited by the extent of the old digital elevation model from 1970, which was produced by Norwegian Polar Institute and is publicly available. So it's this part of coast which is covered by the old elevation model. And the data that I was using for this was firstly the old 1970 elevation model with a 20 by 20 meters resolution. And then I used, for comparison, I used the recent Arctic DEM with a 2 by 2 meters resolution. So I was comparing these two data sets. I also took multiple satellite images from Landsat or Sentinel for the recent years, and also the database of the Norwegian Polar Institute with the shapefiles of all the features studied. So I tried to compile all these different data sources to have one complex picture of what's going on at this specific site of Svalbard. I delimit the glacier frontal positions from the satellite images and the NPI shapefiles, which was pretty easy. And then I used the two digital elevation models, the old one and the Arctic DEM as a recent one. Obviously, I had to make some corrections of the altitudes, as both of the elevation models are using different projections and different ellipsoids, I guess. So there was a bit of work on that, but I finally managed to put these two elevation models to fit one on each other. So then it was pretty easy to compare it. Actually, there are about, I think, 10 or 11 glaciers that are covered by this old elevation model. And I will not present all of the glaciers, but just a few examples to show how does it look. So the first one is Hamberg-Bran. It's actually quite interesting because it's the one with the highest retreat rate, about 150 meters per year during the 50 years of which are covered by the two models and satellite images. Then Markham-Bran, a little bit north, which is the only exception in all the glaciers because this one was shortly like advancing between 2010 and 2010, which is a bit special. It's the only one that was at some stage of the development advancing. Karlbran, it's a nice example of the glacier that is probably turning to a land-based glacier because the frontal position stays more or less the same the last like 10 or 12 years. And the last one, Davis-Bran, which is one of the fastest retreating glaciers. The interesting thing is that we can also prolong the time series using the old aerial photographs from 1930s. So I put also just to show how it could be used a frontal position of the glaciers in 1936, which are basically derived from these like oblique aerial images also provided by NPI. If you look on the surface elevation changes, like comparing the two digital elevation models, the most striking thing is that all the glaciers are experiencing thinning in the lower part, but some of them at the high altitudes they are recording mass gain. They are not thinning at the very highest parts of the glaciers. And again, if you look on the 4 glaciers that I choose, again the Hamberg-Bran has lost more than 100 meters of the ice thickness during the 50 years in the frontal part, and there is some more ice in the upper parts of the glaciers. The Hamberg-Bran is quite interesting because it has a connection with the Hornbran, the big glacier flowing to the Hornsund, the big like fjord. And basically after like few decades, there is only like 5 or 6 kilometers left of the ice, like between the east coast and west coast. So according to some authors, Hornsund should be like in 20-25 years probably connected to the east coast by this passage. So there are some like older studies, like for example this one from Strzelecki et al. From last year, comparing the development of the Hornsund, and it's quite obvious that all the glaciers are retreating quite fast. So it's very likely that this part will be gone. There will be no ice, no glaciers in like 20 or 25 years. It's the same picture from like work of Blavčík in 2013, and it's more or less the same, just showing or demonstrating how fast the glaciers are retreating in this part of Svalbard. Markham-Bran is quite interesting glacier because it has, in general, the highest loss of ice mass, especially in this like northern part and also in the central part of the glacier. Only these few small parts on the western side, the high elevated parts, are not thinning. Bran is quite a good example of the typical glacier in this part. like the lower part of the glacier is still losing the ice. It's thinning quite importantly, but the upper part is more or less stable or even gaining some mass. And very similar to Davis Brand, the last one of the examples. So if we somehow want to generalize the findings, we can say that the glacier fronts of all the glaciers are retreating in average almost 50 meters per year during the 50 years of from 1970 till present. And the fastest retreating glacier is the Hamberg Brand, one that is connecting to Hornsund. In this case, it's up to 150 meters per year, which is quite amazing. So you can see the change even from one year to another quite easily. What is quite interesting that from the 11 glaciers that were originally like tidewater or marine terminating glaciers, 4 of them has already turned into land-based glaciers. They are no more like ending in the sea. They are ending like on the land, like for example this one. When we look at the glacier thickness, like most of the glaciers or all of them are thinning in the lower part. In the extreme cases, it's more than or almost 100 meters of difference in ice thickness. And the upper part gained almost 25 meters in some areas. And the threshold between the loss and gain is typically around the altitude of about 250 to 300 meters above sea level. So we can say that there is quite interesting change in the geometry of the glaciers. It's a very simplified picture, so sorry for that, but the retreat is probably driven by warmer seawater or probably the prolonged sea ice-free season. The thinning of the glacier is probably related to the increase of air temperature. And the question is why the upper parts are gaining mass. So probably there is more snow during the winter. So basically then the glacier changed its geometry in such a way. There are a lot of questions how to explain these kind of changes of the geometry. And one of the things is that because of the thinning, there is probably a decreased basal melting and not so much of the water present on the base of the glacier, which can result in decrease of the flow velocity and then probably accumulation of snow in the upper parts. But it's just one explanation. There might be, well, quite some other reasons for that. I actually found one paper which is using a similar data set on Edgea, on the island east of Svalbard, and they found actually exactly the same spatial pattern of what's going on the glaciers. The really important thinning on the terminus of the glacier, and like very stable conditions in the central part, in the upper part of the glacier or ice cap in this case. So very similar to what I found for the glaciers on the east coast. And there's this other thing with the Markham Brand, which actually experienced a surge, which was reported to start in summer 2009. So this is why it's the only glacier which experienced a re-advance of its frontal position. So you see the 2000 position of the front, and then it advances some 500 meters to 2010. Then it's more or less stable, or again starting to retreat. So, and it's quite well visible also on the digital elevation model difference. So it was reported that this like northern branch of the glacier was the surging part. So you can see quite clearly that it has lost like important amount of its mass in the whole, like not just in the lower part, but also in the upper parts of the glacier were thinning. So basically what's important to sum it up, the massive retreat of the old glaciers was recorded. It with average retreat rate of about 50 meters per year, with some like extremes like 150 meters in case of the Hamburg Brine on the south. And it was quite easy to also see or illustrate the episodic readvance due to the surge events, which was quite well visible both on the satellite images and also on the digital elevation models. And quite surprisingly large part of the glaciers has switched from like tidewater glaciers to land-based. And there is quite a common change in the glacier geometry with thinning of the like lower parts of the glacier and surface elevation increasing the upper parts of the glaciers. So the question is what we can do more, or if we can find something more. And of course, we can probably use the old data set of aerial images from 1930s and use it with like structure from motion techniques to reconstruct like even older digital elevation model, which is the technique that is used in Svalbard like last 5-6 years quite often. So that could be done also. And the question is whether this trend is also present like between 1936 and 1970, if the retreat rate is apparently still more or less the same, but the question is if the geometry changes are also present in this like early stage of the development. So I think that's all from my side, and as I already told, I'm not really a remote sensing expert, so if you have any ideas that might help, I would be really grateful for that. So thanks very much.
My name is Dariusz Ignatiuk from SIOS-KC, and I'm convener for this session. The topic of this session is Arctic apps and hackathon. So we will have the pleasure of listening to 4 presentations. The first 2 presentations belong to the creators of the projects from the top 10 best projects from the Hack the Arctic hackathon. Hack the Arctic was organized by the NRefer community. It was a 44-hour hackathon open to anyone interested to make use of the Arctic environmental data to develop a service or project. The last 2 presentations will focus on applications that can help develop new services in the Arctic. During the talks, you can ask questions in the chat box, but we'll have also time for some questions after the last presentation. So I would like to give a floor to Friedrich Röseler with the first presentation from the Hack the Arctic.
Okay, so let's first say we will have to talk together. So I'm Gregor and he's Friedrich, and yeah, we'll share the talk because we attended the hackathon together. Okay, yeah, let's talk about Policy Bear. Thanks for tuning in, and thank you very much for the invitation. We were very happy to have the possibility to talk here. So let's start by talking about how it all started. It started on the Hack the Arctic hackathon, how you already heard. And we had the idea for Policy Bear. You can see a small screenshot on the right of the prototype we developed on the weekend. And yeah, the feedback was very great. The jury really liked our project, and especially ICOS were really happy and said that they could think about collaborating with us together on projects like Policy Bear in the future. So that motivated us very much to go on with our project, and we want to show you where we are now. So I give to Friedrich for the next part.
Yeah, let's look at what our web tool Policy Bear is exactly. So Policy Bear is a web tool to enable policymakers to create simple and good-looking text graphics from complex environmental data in an easy and fast manner. So our target user groups are not only policymakers, but also any users without scientific backgrounds. So our tool should be a platform for everyone who is interested in environmental content and would like to understand more and better the processes behind environmental processes. So since users, since we would like to access all users, we need to offer a high scientific standard, as well as we would like to keep our tool as private as possible and use only open source software and data sources. The result of our tool are simple text graphics. You can imagine these like text modules that are combined by our software with the results of measurements. So you can choose between different parameters, such as, for example, carbon or methane, carbon dioxide concentration or methane concentration in the atmosphere. And you can select these parameters for different observation stations within the ICOS network and compare these between two different dates. So just simply change detection. And to make these more comprehensible, you can compare these measurements with everyday sizes. And everything is done completely automatically in our software tool. Not only do we want to have simple text graphics, but they should also look pretty so that you can export them, for example, as an image or as a PDF document to be used within the next conference meeting or presentation where you would like to present results that you explored on our website, Policy Bear. So therefore, we designed three different styling themes from which you can choose to style your text graphic. So what about the data that we are using? We are currently using data from any open source data provider where you can download data via a URL. We've implemented currently the data from ICOS that is fetched by a Python API, and all of our data computation takes place on a separate Python server. So we fetch the data, we aggregate it, we upload it into our own database so that users have fast access to it via our website. And this also allows us all kinds of scientific computing that you would normally do with your data when you would be working on some research project. So we are not really limited, since all computations can be done in Python. It should be really easy to use our tool. Policy Bear can be accessed via a public web page from any kind of device. You can use it from a desktop PC or some tablet or a telephone, a mobile phone. And we created our user interface as usability friendly as possible, so that every user should be able to create these text graphics without any problems. And also create them as fast as possible. It needs only 7 clicks to create your own first text graphic. And with our predefined examples that we have on our front page, you would only need 1 click to explore scientific data really easy and fast. So Gregor is now going to show you a live demo of our web application. Feel also free to follow the web link. Yeah,
we'll post the link later in the chat for you to go there. So let's click on the link. Can you still see the screen? Okay, good. Okay, so now we are on the landing page of Policy Bear. You can see there are 2 buttons that we can press from the start. You could start creating right away with this button, or you could first look through the examples. So let's do that now. And there we have like some pre-prepared cards that are generated by Policy Bear. You could scroll through them, and if you would like, you could share them right away, or go in the editing mode and edit the card that is displayed here. But for now, we want to create a completely new card by pressing Start Creating. So now we are in the editor of Policy Bear. And here on the left, you can select the data you want to be displayed. In the moment, there is methane and carbon dioxide as parameters. Let's choose carbon dioxide. And then you can select an ICO station where the measurement is from. You could either pick it from the list, or you could also click on the map button here and select the station from the map. For now, let's pick the station in Munich because that's where we are from. And then you need to select the two points in time that are compared. You could either compare annual values or monthly values. Let's choose monthly, and 2016, maybe June, and 2020, also June. And that is all you need to do, and then you get your first own card. The methane concentration at the ICO station on Peißenberg increased by 0.03 ppm between June 2016 and June 2020. And if you are happy with the data, then you can also customize the look of the card. You can change how the data is worded on the card. So you could also compare absolute values. So now you see the two values at the two time points. Or you could show the difference in percent, like this. And so now you have only a 1% number for the data. And here you can also select an everyday size to compare. For methane, it's cars and cows. This is very much work in progress, so don't be too sure about the number you see here. We plan to increase the accuracy of our algorithms in the future. More on that later. And also you can pick one of 3 themes in the moment. This is the typewriter theme, and there's also the newspaper theme. It looks like this. So you can see that there's a like really fast, relatively pretty card that you could use in your presentation. So if you want to do that, you can press on the share button here, and then you are in the share menu. Here you could download the card as an image or as a PDF. You could go back to the editing mode and customize it even further. Or you could copy the link to the share menu. Just for demonstration, if you would paste this link in some chat or something, people could directly access the sharing mode and go back to editing, for example. Okay, so that was the short demo. Let's continue with where we want to see Policy Bear in the future.
Yeah, so that was the current state of Policy Bear, but where are we with Policy Bear in the future? So first of all, we would like to add some more parameters to compare to from other data sources, and we would like to improve our algorithms for computations and to allow meaningful comparisons with these everyday measurements that Gregor just showed us, cows and cars. Furthermore, we would like Policy Bear not only to be a platform for policymaking, but also as an educational platform. So users, we would like to implement some interactive explanations on every steps on our website so that users can follow these steps and get additional informations on, for example, the parameters on their interactions with climate, environmental changes, etc. And maybe also in the future, we would like to add some more social features, such as sharing or voting your text graphics that you've created with our tool Policy Bear.
So our last question is, how can you contribute to Policy Bear? See two ways how you could contribute maybe. The first one is contribute your data sources. So if you have some data where you think maybe that could be a benefit for Policy Bear, then feel free to contact us about that data. We see only two limitations, what the data need to be. The first one is it needs to have some kind of time series where we could compare two values on two different time points. And also it would be great to have some kind of meaningful comparison to an everyday size. For example, ice coverage could be compared to football fields or something. That would be really awesome if you have some kind of insights or ideas about data that you have. And the other way is you could also just contribute, not just, but you could contribute your knowledge to Policy Bear. If you have insights about algorithms to analyze data and to compute meaningful comparisons and aggregate data, then feel free to contact us about that. We are really happy about any kind of ideas and hints about new approaches. So how can you contact us? This is our contact sheet. Of course, you can visit our webpage. Feel free to go there and try it out. Also, our project is open source, so you could look into the source code at GitHub. We have an email address where you can send us suggestions or ideas. And you can also contact us on Twitter. Those are our Twitter handles if you want to get in touch with us. Okay, so thank you very much for listening, and back to Policy Bear.
Thank you, Dariusz, and nice to meet you, everyone. So we will be presenting our project called NoHaze that we developed during the Arctic Hackathon, and it was developed. All four of us, we developed it. We will show you. And the interesting thing is, we just made there. We did not know each of us beforehand. We just made there randomly, and then we decided to work on this. And at the end, it was a very learning and very nice experience. So I'm now just going to share my screen and take you through our presentation. So can you see my screen?
Yes, now the full screen. You can go into the presentation mode.
Yeah, so as I was telling you, this app was developed by Marika, Dung, Elin, and myself. But unfortunately, Elin could not be here physically, so she just recorded the introduction part of this presentation. So I'll play that, and after that, Dung will tell you about the app, and then I'll come back with the app backend and how does it work. So let us start with that introduction, which Elin recorded for you.
Hello, I'm Ellen, and this is the project me and my teammates made during the Hack the Arctic Hackathon. We were given one weekend to create a project that incorporates Arctic data, and we chose from the hackathon challenges to create a service for citizens on a phenomenon called Arctic haze. And so the app NoHaze was born. From the start, our key purpose with the project was to track pollutants and give us an output to the user, an evaluation on how dangerous the pollution levels are. We ended up on tracking 3 pollutants, which were sulfur, of which about 90% of Arctic haze consists of. Sulfur affects cloud formation and leads to an increased reflection of sunlight, which generally has a cooling effect, but during the winter, when there is no sunlight to reflect in the Arctic, the clouds trap infrared radiation from the surface. Then carbon, which is the remaining 10% of Arctic haze. The carbon is helping out warm up the Arctic faster than any other region. And then finally, we track nitrogen oxides, which are ozone precursors that can also be detected in the Arctic haze in small amounts. Then this is a picture taken from the Zeppelin station on Svalbard, where you can see the Arctic haze in the distance. It has this red-like hue, which is caused by carbon. Well, all of this then begs the question, what is Arctic haze? Well, it's a particularly persistent form of air pollution that occurs at higher latitudes in Arctic regions. It contributes to climate change as well as hazardous air quality that directly impacts Arctic communities. The haze causes limited visibility on the horizons of what had been previously very clear Arctic skies. It is most visible in early spring. Some Arctic pollution sources are fossil fuel emissions from industry and boat and ship emissions, then also smoke from forest fires. Arctic haze is still considered to be caused from pollutants solely from human origin. It is important to track Arctic haze because the Arctic helps to regulate the world's temperature, so as more Arctic ice melts, the warmer our world becomes, which in turn leads to even more melting ice, and so the vicious cycle of global warming continues. With effects like rising sea levels and reducing the albedo effect, which is the process by which thermal energy from the sun is reflected back into space. Many people also perceive the Arctic as a pure and clean region of Earth, but the pure and clean landscapes may soon become a memory as pollution travels more and more and leaks into the Arctic regions. Because of the Arctic's global effects on temperature and extraordinary sensitivity to pollution, we believe the Arctic haze could be used as an indicator of global warming, and more awareness should be spread on its existence.
Okay, so now I will continue. Over the weekend of the hackathons, we developed a demo using Python, and here's how the app's NoHaze look like. We prepare a short demo video. Here's the main page. You can see it will display the general air quality of your current locations. And if you want to find more information, you can go to the search page where you can select your pollutant species and then input their time frame and then your locations. Then the app will retrieve the data on that certain pollutions, and it will display a complicated graph and also a simplified graph. And this data will be compared to a guidelines levels to display like is it hazardous or not. And here you have the info page, so you can learn more about the Arctic haze and also how to help. And we also have submission features, so the user can submit their own observations, so we can confirm our data. And lastly, we have the notification to warn the user if they are in a danger zone. So that is the app, and here's the if you can move to the next slide. Okay, so here's how it works. The app will collect a few simple data like location, time, and the pollutant species, and it will send requests to a ground station or a satellite imaging to get their data, and then it will retrieve the complicated data to graph, and then also simplify that data to a more user-friendly version, so the user can know more information about that pollutants. Yes, you can move on. So our goal with the app is to determine how much air pollution is present in a certain location and certain time frame, and to determine is it hazardous or not. And with this data gathered, we can help the user of this app to make educated decisions. And finally, we want to raise awareness and encourage community science efforts to study the Arctic haze and how to help it. Okay, so next part is about the front end of the apps. Over the weekend of the hackathons, we created it using Python with the tkinter module. But later we are working on a new version using Shiny in R, because the backend of the app is currently using R to pull data from different server. And like on the right, you can see like how it should look like. And that mockup is made by Portal.io. And the goal of the app is because our target audience is like everyday user, we want to make the experience as easy and as convenient as possible. So the goal is to make it clean and easy for the user to see the data and also to contribute their observations. And finally, we want to make a consistent look for the NoHaze brand. Okay, thank you.
So as Eleanor already told you our motivation behind this project, and Dung also told you what were our objectives, I'll now show you how does the app work. And this app initially was written using the Tkinter module in Python, but since the app backend was always written in R, we thought of making the app everything in R using the Shiny module. So we will now show you step by step how does the app work. So this is the, I hope you can see my RStudio page, and it first just goes to the working directory and then loads the required packages, which are Lubricate and Shiny, two very useful and user-friendly ones. And then the app front end. So basically when the user opens the app, he or she gets to see these front end, where you see these drop-down options. These drop-down options are for the station where the user is interested in, and for the particular pollutant species, and then the visualization window. Because we provide the visualization like in, okay, I'll tell you step by step. So at present, the user can only select between Hutiala and Helsinki. So either of these the user can select. And also in terms of pollutant, the user can select among carbon monoxide, dioxide, sulfur dioxide, and NOx. And then the visualization window at present are offered for 3 durations. That is for the last day, for the last week, and for the last month. And once the user makes the selection, then the app confirms to the user about his or her selection that you have selected Hutiala and NOx and the week. And then the app actually, in the app backend, the app actually reads these options, and then the app runs it. And when we run this backend, in the backend, the app actually fetches the data from the smear station, which is open source, and then it plots it. And once the plotting is done, then the second front end, the second interface of the app appears to the user, which looks like this, where the user can see the selected pollutant trend at the preferred location, which was Hutiala and NOx, and for the last week. And then the user has the option to, so basically this is the app backend, and user has the option to see how did that particular pollutant varied at that particular location for last window, that last week or last day or last month. And based on that, the user can make the decision whether to venture to that place or not. And at present, the app also provides some guidelines that whether the level of pollutants there is safe, or it is orange, or it is red, depending on the available alerts from EPA, US EPA, or WMO, or different air pollution agencies. So we have a separate section for that in the app. And okay, and that was the app backend. And now, where do we want to see the NoHaze in future? So as I'm talking to you, the app is still in a prototype phase. And we must admit that it is not yet available as an Android app or something so that you can just download it and start using. We have to spend some time to be there. And while we are at it, we also want to enhance the app features by enhancing these following points, which are basically, we want to add satellite data also, which are mostly open source, along with the smear surface measurements. So basically, we can add Sentinel-5P or any other satellite data. And then this will serve both two of our purpose. First of all, there can be, scientifically, there can be comparison between the ground level measurements, which are of course very local in nature and mostly have a larger or more or finer temporal resolution compared to the satellite data, which has coarser temporal resolution, but they can cover a wide area. So we can also see scientifically how well do they compare to each other. And then in terms of service to the app user, it can tell us about a larger area, whether this particular haze event is prevalent there for a large duration of time over a large area. And so the user can be having a more comprehensive knowledge about that event. And secondly, we also want to increase the pollutant species to be tracked for a more comprehensive picture of the severity of the haze. Having said that, we are considering to include PM1, PM2.5, and PM10, which are very crucial, or which are very notorious rather, for pulmonary diseases, and which should be avoided. And then we also want to work on making the app interface more fluid and more helpful. So that is our plan. And then if you are interested in the dataset that we have used, it is all available here as open source dataset. And then if you want to know more about our project Arctic Haze, you can find it more on the Arctic Haze in general, you can find it here. And if you want to know more about our project NoHaze, then you can always visit this Hack the Arctic Hackathon page, where the details about our project and then the GitHub repository and the video, everything is hosted there. So we thank you for your attention, and we will be happy to answer any of your, if you have any question. Thank you.
So the app I'm presenting today is something that me and Adrian made as part of the Hack the Arctic Hackathon that happened a couple months ago. We had not met before either. We met simply through the social media meeting thing that they had on the application. Also like to note that I work for a group called Face It. I don't have any of their logos on this talk because we kept all the pictures out of it to keep the size of the app as small as possible. And this is running on a free server, and it is of course open source, and I can share all the links for that after the talk. So what we're really looking at today is I'm just going to go through the documentation very quickly that explains really what the data sets are that we used, and then I'll show how the actual user interface works. So when we were putting this data analysis together, the idea that we really had was that we wanted to create a proof of concept, right? This isn't an app, but we have no intention of ever putting this on Android or anything like that. It is specifically a Shiny application that is front end in R, and the data analysis, which are static, they're not dynamically done, was done in Python. And this was all done across those two languages through GitHub together very seamlessly. I was pretty happy about how well that worked. So we wanted to create something where it would be more for stakeholders, not necessarily scientists, certainly not physical scientists, who would want to know what are the annual averages, the anomalies, and the long-term trends in some important physical variables around Svalbard, the Svalbard archipelago. So we basically just relied on the ERA 5 product. From that, we took air temperature, sea surface temperature, sea ice cover, and then there's mean sea level pressure in there as well. Snowmelt did not make it into the final version. We were busy writing up the documentation as I was busy trying to code these last little things in there as we were getting close to that 2-day crunch period. So sea ice thickness is not in there either. For vector data, that basically just means shape files that we use. So there's a couple of different coastlines that we used. We did not end up with a permanent snow or ice mass, but we do have glaciers in there. And we weren't able to show differences in terminating points of the glaciers over time, unfortunately. Point data, we did not end up using the Polish Polar Station data, but we do have a couple of points from the Global Historical Climatological Network in there. And if there's a bit of time at the end of this talk, I'll show what those look like, but really we're focusing on the remotely sensed data because that's the topic of this conference. So what does this look like, right? Well, first up, oh no, this looks terrible. And the reason for that is that this is simply a HTML file, right? So this is running in just my Firefox web browser. I'm running this locally. I'm not running it on the live server. It's a little bit faster when you run it locally. And so, there we go. Oh, it's being difficult for me now that it's running live. Let's just resize it here. So the landing page then is first the trends in data. And so up front, we use the trends in air temperature because it's the most dramatic picture, right? And so when we look at these data, what we're seeing is the trend from 1979 to 2020. And the values themselves, as you mouse over each pixel, these values are the decadal trend, right? And so when I first saw this, I thought that this couldn't possibly be correct, right? These are I thought these were way too high for my work. I specialize in marine heat waves globally. But, you know, when you click at these and you look at the time series, like you take this one, for example, a decadal trend of about 1.4 degrees Celsius per decade, you see that in 1979, it was about negative 1.4 degrees. And the highest point, which is around 2016, is about 6.9, right? So that's about a 7.5 degree difference over time. And 1.4 degrees per decade at 40 years, you know, that's 7.6 degrees. So the air temperatures really are changing that quickly. And we can look at the trends in other things too, for example, like let's look at sea surface temperature. And so then we see again, you know, this current here, as we know, is warming up very rapidly. But again, you know, 1 degree Celsius per decade, the global average is about 0.13, depending on who you talk to. And so this is almost 10 times the global average. It's 8 times, which is staggering. It's yikes. So that itself is already useful to somebody that maybe isn't very familiar with the Svalbard region. Like I only started working in it earlier this year, to really get to see, here's a crash course of how rapidly this place is warming up. And you can look at anomalies as well. So now we're dealing with annual data. So these are going to be the averages over the year. So this is the temperature, sea surface temperature anomalies for 2020, for example. And so let's click on just somewhere in Isfjorden here, and we can see what the temperatures have looked like over the last roughly 40 years. And we can see some big differences. So here's 2020, 19, 18, 2017 was a very warm year. 2015, a bit less so, right? If we want to look all the way back in time, we can see, you know, what do these anomalies look like? You can see here that the open ocean was colder compared to, you know, today, which isn't very surprising because that is that trend over time. I find it interesting to look at sea ice cover, but then anomalies for me don't make as much sense. And so this is when looking at mean values becomes a bit more reasonable. And so I use the Viridis color palette for this. And let's reduce the resolution of the coastline, and we'll remove these stations so that the pictures render a little more rapidly when we want to see them as an animation. So in Eastfjorden, for example, Icefjorden, the ice cover really sort of just disappears after about 2008. So I think it's interesting to look at an animation around that period. So we'll go back to 1999, just for example, where the average annual percentage is about 34%. And as we go forward in time, you can see that this sort of disappears after 2008. I'm sure that a lot of people that are here now know this, but for me, you know, I'm still getting to know the area. So I found this sort of thing to be very useful, even though I am really a physical scientist. And here we go, 2008, and then now we're down to basically just 0%, maybe 1%. It ticks back up to about 6 or 7 in 2020, which is interesting. And so this is the merit of this sort of thing. And this is running live. And so really, this is the sort of tool that perhaps SIOS or someone else, it's not 3D, which I thought was really cool in Erik's talk, those tools, I wasn't aware of those. But this sort of basically two-dimensional representation of data, it really doesn't require any serving power. It does need to be served on a server. It's not a static website, but I think the whole thing is like a couple megabytes, you know, it's really just a very derived data products. And like I mentioned, we do have some station points in here as well. So we can go to Nye Allison, for example. And this is just really Mickey Mouse out of the box stuff, right? So this is just, I think this is monthly. Yes, these are monthly average temperatures at the surface in Nye Allison with the trend line, you know, hyperimposed over it so you can see what that is over time. You know, basically the winters are just getting warmer. And just to demonstrate that this is an HTML document, so basically the sky's the limit. You can put photos in there. You can do anything that you might have seen on any other website. You know, tabularized data, for example, if you wanted to see what are the warmest Julys on record, 2020, unsurprisingly, is the warmest. And in the top 10 here, you know, most of them are in the last 15 years, with the exception of 1985. And there's heaps of stuff on here. So I'll put the link, please have a look at it. It's fun to play around with, or horrifying, depending on your take on these sorts of things. And it's just something to explore, something to get a feel for the data, what's going on. And it's not really designed to be an actual scientific tool, right? But that's not really its point. So I'll stop it there, keep it short and sweet, and look forward to any questions later.
Perfect. So yes, hello everyone. I'm going to talk about IcySea today. It's an app that provides to polar navigators real-time sea ice information. So just a bit before who's behind this app, IcySea. So it's Drift Plus Noise Polar Services. We're a spin-off company. We're based in Bremen. We're a spin-off company from the Avi Wegner Institute for Polar and Marine Research. And we're also supported by SIOS-KC. So this is the team that's behind the app. So Paul and Bernard are software developers mostly. And Ignatiuk also helps in developing, but also in the research on new sea ice information. Lasse is the founder of Drift Plus Noise. I think he's here with us today. And he's also responsible for ensuring a sustainable growth and management of the company. And then I'm part of the team. I joined in December, and I'm mostly working for outreach and collecting user feedback on IcySea. We also have our partners from the Meteorological Institute of Norway. They help us with the ice drift forecast on the app. So IcySea users mostly for fisheries, tourism, any research and shipping, bulk shipping, or any vessels that are coming in the Arctic. So this is just a short video of my master's thesis project. So it's the archipelago Svalbard in the middle. In green is the position of fishing vessels. And in yellow is the position of expedition cruise vessels between 2012 and 2019. So it's just to give an idea of how close in the end these maritime activities around Svalbard really interact with the sea ice variability throughout the years. There. So kind of the reason why IcySea started was with my colleague Lasse Rabenstein. He was on board a vessel around Svalbard, and there was no ice information on the navigation screen. This is what they saw, and he kind of had the idea of like, wouldn't it be great to actually see directly near real-time sea ice information. So while navigating in the Arctic, you need the weather data, sea ice satellite images, ice charts, forecast, and much more. So with IcySea, we focus on satellite images, sea ice concentration, and ice drift forecast. So before I show you the app, just wanted to point out that it's not just another web page, which some of our users have thought. It's a progressive web app, so you can install it directly on your devices, your computer, your Android, your iPhone, or your tablet. And it's not going to continuously ask for data. So once it's installed, it's not going to be using data connection unless you're updating the images. Here's just approximate data usage. So if you're at sea and you need information, so we recommend that the app is installed while you're still at land or at port. Because it takes about 5.7 megabytes of data. Sea ice concentration, 136 kilobytes. Ice drift forecast, 176 kilobytes. Sentinel-1 images with low resolution, 28 kilobytes, and Sentinel-1 high resolution, 1.7. Then we also have information on the tile age of each Sentinel-1 images. And all this information you can find on our website, which I will put the link at the end of the presentation. So now I'm just gonna I'll show you the app, which I've already installed on my computer. Can you still see do you see the app or still my presentation?
Still the presentation.
Okay, then I will just do this. There. So this is a IcySea app. So we have, for the moment, it's around the archipelago of Svalbard, which we have here in the middle. So here at the top right are the different layers that we have for the moment. So sea ice concentration. And here you have the timestamp. So this is actually from a few days ago. So you can refresh it on this little arrow here. And this is the sea ice concentration from today. And you have the different colors which reflect to the different sea ice concentration from 0 to 100%. And then in addition to this, you can have the, sorry, I'll just mention now actually that the sea ice concentration, this data is updated up to 8 times a day. So really it's the latest sea ice concentration information that navigators can have. We include also the ice drift forecast. This is done from our partners at the Meteorological Institute of Norway. Again, I'll just refresh this at this little arrow to have today's drift forecast. And then you have the little legend at the bottom left that it's from yesterday. So yesterday would be day 0, and then how it continues, how this ice will drift in the coming days. So I'm just going to zoom on one of these little guys of the drift ice. So it also gives you the direction with the arrows of each point of where the ice is going to drift over the next days. And then finally, you have the Sentinel-1 images. So probably you saw there's this, this blue grid around the archipelago. And this is where you have access to Sentinel-1 images. So I'm going to show you a few here. So you can have them in low resolution. So you have to select them individually as it's, those are the ones you'd be interested in. And if you're in low bandwidth connection, you'll have access quite fast. I'll take this one as well. So I'll zoom in on these guys. So yeah, these are the low resolution images. You can really see the sea ice swirling around here. And let's say I want to update to the high resolution if you're really navigating close to this area. So I really get a clearer image. So there is some tricky parts, I guess, of analyzing Sentinel-1 images. These ones are quite clear, but sometimes the backscatter colors, well, not colors, sorry, from white and black can be quite confusing. So we always recommend that for users to compare both the Sentinel-1 images and the sea ice concentration behind to be clear if this patch of gray or white, is it sea ice or open water? So yeah, the Sentinel-1 images are updated to, sorry, I'm just hearing some background noise. You can have the timestamp of these images. So show tile H here. So these images are a day and 5 hours old. The update is normally around 4. So hopefully later this afternoon, there will be new images that would be less than a day or less than half a day old. And then for each layer, there's some information. So if you're unfamiliar with sea ice concentration data, you can look here, the 10% rule that below 10%, the sea ice concentration won't necessarily show. And that's where you can also kind of play with the Sentinel-1 images. And yeah, there's lots of information on how to interpret these. And the same of the ice drift forecast, with the data sources and guidelines. And the same for Sentinel-1 images, some guidelines, some examples. So you can always go there. And if you have any questions, you can always email us. Our emails will be at the end. So I'm going to go back to my presentation. Sorry for the back and forth. So our development of ICC is strongly based on user feedback, because we really want to make an app that users need and that they will find useful, and not just kind of only develop our ideas of what we would think are useful, but really have the navigator's opinion. So here are some ideas that we had and we presented to some of our users a few months ago. So first of all, soon you will be able to see your own position directly on the app, and also extract the coordinates if you want to use it on another device or even on your screen on board. And slowly our goal is to have the global coverage. So this month we'll be releasing the Kara Sea region, and there will be some ports as well and some other new features. So I will put some links at the end anyways. So this is for sure what's going to happen soon. And then for the future, what should we implement next? It's kind of a question to you. If you have preferences, if you think you're going to use this app on a research cruise or whatever, feel free to or email us or even write in the chat. We can figure that after. So to include more navigational tools and more information layers are our goals. And then like which ones would that be? So navigation and tools would have to maybe include AIS information. So you could see directly which other vessels are around you. So this could be useful if you want to know exactly how the sea ice is. You could just call directly that vessel. They will give you how the ice conditions, or in case of emergency, you can see who's around you. And then on more for your own cruise, you can have the individual markers, so your position, plot your next route that you're planning to sail, and distance them and measure the distance of the areas. And then as information layers, we'd like to include official ice charts. So here's an example, bottom left, of the Canadian Meteorological Institute with the ice chart of the St. Lawrence Bay. So to kind of have an extra layer of these ice charts, which maybe captains or navigators are more used to, so then to kind of help them with our layers as well. We would really like to include optical satellite images. This had a lot of success a few months ago when we presented this to our users. Was kind of the main demand would to develop this, and then also include more weather data, so wave and wind information directly on the app. So it's really to have everything in one app, accessible with low bandwidth connections. So really when you're sailing in remote areas, let's say even north of Svalbard, to have access to information. So yeah, if you want to help us take part in the development, you can register today. So registration is free. You'll receive a token, you put it in the app. If you have any troubles with registering, just contact me. You have my contact here, stocker@jiffnoise.com. Or if you have a more general question, you can ask directly at info@jiffnoise.com. You'll reach the whole team. So as I said, registration is free. The Svalbard area is free until the end of the year. And yeah, feel free to share it with your colleagues and give us your feedback. Would be really helpful. Thank you.
Climate change in the Arctic is amplified and accelerated. Climate models reveal that Svalbard is situated in the core area of this Arctic amplification. A credible climate study, however, requires long-term synthetic remote sensing data to characterize the changes. In this study, we consider the Arctic amplification over Svalbard from a remote sensing perspective. We quantify the changes in the Arctic atmosphere using a diverse set of products covering at least 2 decades. Surface air temperature at Svalbard is rapidly rising since the 1970s, especially in winter. Century-long observations at the Svalbard airport show a persistent surface air temperature increase by almost 10 degrees in winter, or increase by 5 degrees for the annual mean. Most of this increase has occurred since the 1990s. That is during the era of intensive satellite observations. In the sense, satellite remote sensing is a key to reveal the full extent and complexity of the Arctic amplification over Svalbard. We understand that the local temperature rise is driven by large-scale Arctic warming. The most influential drivers are related to the meridional heat transport and the sea ice extent reduction. The meridional heat transport occurs in 3 different pathways. Svalbard warming has been robustly associated with the North Atlantic pathway that opens a gate for Atlantic heat into the Arctic, and observed more than 30% of time. Arctic warming is not surprising on the background of the global temperature rise. The temperature change in the Arctic is, however, strongly amplified. Observations reveal the largest amplifications over marginal sea ice areas, but there is still a divergent consensus, as Cohen et al. Called it, on whether sea ice retreat caused this profound climate phenomenon. We may quantify the amplification as a simple difference of the temperature anomalies averaged over the northern hemisphere and an area in the Arctic. Although amplification measure is simple, its reliable estimation could be a complicated task. Satellite data products are not covering sufficiently long time periods to identify climate anomalies on the background of intra- and interannual variability. Only recently, we got an analysis synthetic data products that cover 2, 3, 4 decades of observations. One may mention here diverse analysis products that blend, or better to say assimilate, satellite observations. It has been shown, however, that reanalysis increasingly deviate from a real climate as observational constraints are being relaxed. Moreover, reanalysis cannot provide vital details of small-scale physics and dynamics of the climate change. Climatic satellite datasets have emerged. They combine data from different satellites and sensors that are not identical. Hence, synthesis and intercalibration are applied. Unfortunately, it has been shown that trends are significantly sensitive to the methods. We will cover here the records from the University of Alabama upper atmospheric temperature datasets, the MODIS land surface temperature dataset, and cloud datasets. Beginning with the upper atmospheric temperature, the tropospheric MSU dataset connects shorter datasets from a succession of NOAA satellites. The current version 6 has been recalibrated to agreement of the recent temperature trends. The trends in the satellite data have been increased by more than 0.2 degrees per decade. We calculated the Arctic amplification over Svalbard using MSU-TLT dataset. Since 1990s, Svalbard atmosphere shows consistently larger temperature anomalies, although recent heat waves in Europe, Siberia, and elsewhere offsets the warming in the Atlantic Arctic sector. More accurate as well as more widely used data are coming from land and sea surface remote sensing. MODIS data products are actively explored. In combination with other earlier sensors, they are used to create 40 years of land surface cover records. As you can see, the surface data reveal a persistent bias toward colder than observed temperatures in the Arctic, including Svalbard conditions. The bias could be explained by negative surface heat balance under clear sky atmosphere that leads to strong surface cooling and formation of surface-based temperature inversions, where temperature jumps by a few degrees over the first meter of air. The lowest atmospheric stratification is highly sensitive to physical soil characteristics, land cover, and relief. Lower and dark areas may trap the heat in a shallow atmospheric boundary layer that results in stronger temperature increase than otherwise would be expected from such variations in the local heat balance. In high latitudes, where the stable atmospheric conditions are dominant, it may create large diversity of microclimates and therefore habitats. Still, At larger scale, the Arctic amplification has been linked to the changes in the Arctic marginal ice zone. Sea ice retreat opens moisture and heat exchange with relatively warm water surface. It has been shown, not with satellite data yet, that the strongest warming is collocated with the areas of sea ice retreat. One of such significant areas is to the east of Svalbard. Therefore, a certain priority shall be given to studies of the marginal ice zone with satellites. There are several recent and planned missions that would help to research in this direction. From the climate perspective, monitoring of sea ice, sea surface temperature and other parameters is in good shape with several decadal scale data products available for analysis. However, the marginal ice zones still cause problems and contribute to uncertainties. Especially important to monitor climatic sea ice cover changes along logistics sea routes such as in Isfjorden. The sea ice retreat is linked to the changes in cloud cover fraction. There are still differences between satellite products significantly larger than interannual variability. In particular, the lower stratus clouds that are frequently have low contrast with this ice and snow cover are difficult to detect. At the same time, the stratus clouds control the downward long wave radiation and thus the Arctic heat balance. Changes in the total cloud fraction are often highly correlated with climatic phenomena. At Svalbard, they are correlated with meridional atmospheric advection, cold or warm outbreak events, and the following air mass transformation. In this respect, clouds are organized in large cloud fields, where the role of vertical turbulent convection is increasing with distance from the marginal ice zone. The convective cloud fields are related to turbulence self-organization in the lower atmosphere. Despite of abundance of data and good understanding of physical processes, the cloud field analysis for climate research is still underdeveloped. We hope that wider application of the machine learning and pattern recognizing methods will bring progress in this area too. Summing up, we are approaching the era of accessible long-term satellite records for climate analysis. It will help to create a coherent picture of observed physical changes down to the user scales and larger scale dynamic phenomena such as the Arctic oscillation and amplification. This coherent picture is needed to harmonize a choice of sustainable development pathways for Svalbard with the observed and expected changes of climate factors.
Hello everyone. Our report is called Year-Round Thermal Infrared Measurements of Methane Emitted by Arctic Seas. Methane is a greenhouse gas and it takes part in Arctic warming as well as global warming, and that's why it is important. First, my name is Leonid Yurganov. My co-authors are from California and Alaska. First, about methane sources and sinks. Sources are natural gas and permafrost. Also, methane hydrates are formed under high pressure and low temperature. And methane dissolves in seawater, lifts up to the surface, and on the way is consumed. Dissolved methane is consumed by bacteria. For methane, there are two natural barriers to enter air. First is pycnocline. It is a warm and salty layer that exists mostly in summertime. And second, in winter, is ice in some areas of the total Arctic Sea that are under investigation. Two kinds of satellite data. They differ, these two kinds differ by the radiation used for short wave infrared near to micron. Solar radiation reflected by the surface is used for measurements of gases, including methane. But this mode is not quite convenient for the Arctic because of low angles and low reflectivity. Another one that used by us is thermal infrared radiation, and we use the radiation near thermal infrared radiation near 8 microns that is usable for day, night, summer, winter, sea, land, so that is very useful for us. What do satellites see? You see here summer, winter, May, summer to May, July, and winter, November, December, January, distribution of methane for 2004-2019, and for 0.04 kilometers layer. There is a trend during this period, 15 years, so it is accounted, so the same color means 45 difference in concentration. And the very obvious difference between summer and winter. In summer, no changes, absolutely global trend, and no changes between different areas of the sea, but very clear red spots in winter, especially at the end of this period. And linear trends for all this period is on the right. This is summer trend, close to 3 ppb per year. This is global trend, also low trend and high trend, about 5.5 ppb per year in some areas in winter. So it is evidence of emission of methane from the sea. What measurements of dissolved methane are available in summer? Because in winter there are no measurements at all. And this is an example very for area near Svalbard, from Svalbard to Bear Island for August-September 2015. They measured high concentration in deep layers, but above pycnocline, this pycnocline location, the concentrations are low, and therefore the flux is low after the breakdown of the pycnocline. It is expected that flux would be higher. Temperature data available for this box. It is western side of Barents Sea. The trend in deep potential temperature, so near bottom layers of the Barents Sea, the trend is very significant using different sources of information, and 1 degree change during last 20 years. Okay, and also interesting for us is decline of ice concentration for Kara Sea is here, and the distribution is here for beginning and end of period of measurement. And this is difference between them. And change in ice concentration is maximal to the east of Svalbard, and also high for north of Kara Sea, and for all this area, northern Barents Sea, northern Kara Sea, the change is very significant. So much higher than for Laptev Sea, East Siberian Sea, only in Chukchi Sea it is also a little bit higher than zero. Next, let's compare the change in methane with changes in mixed layer depth, seasonal changes. These are months, summer, December in the middle of the scale, and we calculated difference in methane concentration between the box in the Barents Sea and box in Norwegian Sea. And this difference grows with months from summer to winter. In winter, maximum of this difference. And compared this difference with this seasonal cycle of methane anomaly with seasonal cycle of mixed layer depth. So in summertime, the mixed layer is very shallow. It's not higher than 30 meters, but it is as high as 300 meters in winter. That means that in winter, total column of Barents Sea is mixed, and the barrier is for methane is minimal. So that explains change in methane anomaly. Trends in 3 boxes for whole period of measurements of Earth and EASI. It's a little bit shorter. For water surface, and ice surface. For it's Kara Sea, Barents Sea, Norwegian Sea. And we see that this in Norwegian Sea especially trends in winter and summer the same. In Barents Sea, the winter trend is a little bit higher than in summer, but in Kara Sea it's more significant, and most significant was calculated. The trend was observed in Kara Sea by EASI instrument. It's twice as large in winter compared with summer. So the amplitude of seasonal variations grows with years, and this is explained obviously by decline in ice in Kara Sea. And also very interesting to look into trend in mixing layer depth, MLD. This is seasonal. This is seasonal variations of MLD from summer to winter, and if we look especially November, December, January, means that during this period of time, the mixing becomes less and less. So low MLD means low mixing, and this is not observed during the winter maximum of MLD. So it is explained by this seasonal cycles for the beginning, for beginning and end of period is shown here, and we see that seasonal cycle of MLD shifted from left to right, from the beginning to end of this period. So this is explained by a period of high stratification in summer, lengthening and negative trend of mixing intensity offsets the flux increase due to temperature that we've seen before. How much methane is emitted by Arctic seas annually? We estimated it for 3 instruments, and synopsis is here. Land emits 25 teragram per year. Total Arctic land, total Arctic seas, 2/3 of that, and Barents and Kara seas contribute approximately half of methane in the seas emissions. Other areas are much lower. What do we have on the bottom line? Most of methane emission from the Barents-Kara seas occurs in winter after the breakdown of the pycnocline. And winter flux grows with years. Satellites show that in the northern Kara Sea and also northern Barents Sea and close to Svalbard, methane concentration since the beginning of the century faster than global trend. And the decline of sea ice cover is the most likely explanation of that, for the areas with perpetually covered by ice in winter time, early winter time. But Western Barents Sea open with open water increased just moderately. So the temperature increase by 1 degree Celsius for 20 years was the effect of this temperature increase was offset by freshening of surface water and increasing of stratification during this 20 years. And the last but not the least conclusion, and that the Arctic seas, Arctic Ocean is responsible total Arctic Ocean responsible for approximately 2/3 of the land emission. So it's a very important source for the Arctic. And the Barents-Kara Sea is the main player, and the contribution and the effect impact of this methane increase, high methane should be taken into account in the models for warming of the Arctic, especially around Svalbard. Thank you very much.
Okay, thank you. So I'm going to talk about 2 separate but related things. I'm going to talk about the potential of calculating sea ice drift from passive microwave data on swath maps rather than daily maps. And then I'm going to talk a little about looking at sea ice drift calculated from wind speed using the free drift model, which can be useful in the summer. So sea ice is extremely mobile, pushed by winds and ocean currents. And this is a really nice animation, which I have to thank Thomas Laverne for. And in fact, most of the pretty pictures in this presentation, I have to thank him for. So it's showing a brightness temperature map from AMSAR 2. And it's a beautiful view of the sea ice moving down the Fram Strait and generally moving around. So ice drift exports ice to and from different regions. It alters the thickness distribution. So it's really vital to monitor sea ice, both for ship navigation when you have leads opening and closing, and you can have regions where the ice is crushing together and getting thicker. And it's also very important for climate studies. So how is sea ice drift calculated? In all cases, really, it's calculated by taking two different maps, different time points, and matching the features between the maps with maximum cross-correlation. So this map here is OSISAF's low-resolution sea ice drift product and from passive microwave data. And the algorithm that's used here is Thomas Laverne's algorithm, which is continuous maximum cross-correlation. So it uses fractional pixels rather than whole pixels to remove some of the quantization noise. And something else about this map is that you notice that there's black vectors and purple vectors. So after the initial cross-correlation, there's a quality control step where rogue vectors are identified and replaced by interpolation. So this is a summer season map, and sea ice drift calculated from passive microwave is less reliable in the summer. So you can see that there's quite a lot of purple vectors where they've been interpolated. So sea ice drift maps from passive microwave are low resolution, and all products to date use daily brightness temperature maps in order to calculate daily ice drift maps. This is different from optical and infrared and SAR, where the sea ice drift is actually already calculated between two swath maps. So this is work led by Thomas Laverne in preparation for the SIMA mission. And he was basically wanting to investigate whether it would be more efficient whether there's advantages in calculating on swath to swath rather than passive microwave. So for this work, AMSAR 2 data was used, and the principle was just to calculate the daily maps with AMSAR 2 and calculate sea ice drift maps from swath data with AMSAR 2, and then validate these both separately against on-ice buoys. So I've included a map of sea ice buoys from the International Arctic Buoy Programme here, which shows that there's quite a good coverage of ice buoys, and these are vital for the validation step, but it shows really why sea ice drift isn't just directly measured by this data, because the coverage isn't great in all regions, which is why it's important to be able to calculate the sea ice drift from the satellite data. So here I'm showing an example of how it looks when you calculate these maps based on the intersection of two swath maps. So in each case here, you've got a static red swath, and you're showing the intersection with a variety of blue swaths. So in each case, this green intersection shows you the geometry of the final map that you would get. So when you're calculating ice drift between two swath maps, you end up with these sort of fractional maps. So the advantages of calculating sea ice drift on swath maps are that there's not really a delay where you're waiting for the daily maps to be made. You can immediately calculate on whatever swath maps you have that cover the region you're interested in. So it really reduces the time delay before products are available. You also get many, many more vectors every day because you can calculate between any two intersecting swaths rather than just one daily map. And you can see here that in the period, there's 2-day period in each case, and you can see that there's up to around about 100 different sea ice vectors. The coverage varies, and for AMSAR2, there's quite a large pole hole, which won't be an issue with SIMA. And the third advantage is that in the winter, at least, which is when this method is most reliable anyway, the swath-to-swath vectors, sea ice drift vectors, have a better accuracy validated against the drift buoys than the daily mapping. So in this plot here, the bars are the RMS of the daily maps compared to the buoys, and the filled in region is the swath-to-swath vectors. So you can see that there's a variety of drift durations for the swath-to-swath maps. But for 24 hours and 48 hours, and really over most of the time range, the swath-to-swath is more accurate. You can notice that the RMS is actually a little greater at 36 hours. And this is actually because it turns out that about 36 hours tends to be when the swaths, the angle between the two swaths will be around 180 degrees. And that's when your geolocation errors are going to have most effect on your results. And for swath-to-swath maps, it will be important that the geolocation is accurate. And yeah, the last thing I was going to say was that actually it's not really surprising that swath-to-swath gives you better accuracy, because when you're not stacking an image to get a daily map, then you're not sort of blurring out the motion that you're then trying to identify by cross-correlating the features in the images. So the conclusions to this are that it's going to be recommended to use swath-to-swath for mapping sea ice drift with SIMA because the products will be available faster, there are more sea ice drift vectors, and they'll have higher accuracy. SIMA is also going to have big advantages over AMSAR2 with higher resolution, wider swath width, no pole hole. And it will be very important that the geolocation is accurate in order for swath-to-swath sea ice drift mapping to be good. There's probably some advanced work needed, because if the users are used to using daily maps, then they may need training and adaptation to use the swath-to-swath maps. And because there are also so many swath-to-swath vectors available every day, there needs to be some filtering step to select the best, which will probably depend on the angles between the swaths and the time duration, the time elapsed between the two images. And finally, there'll need to be code written to actually select and optimally combine swath-to-swath maps into daily maps for the uses where daily maps are required. And I highly recommend to go and read this paper, which is going to be out soon. And then I'm going to quickly talk about calculation of sea ice drift from wind speed, which is something we're investigating using the free drift model. So this is a model which links sea ice drift to wind speed with the assumption that there's no internal stresses in the ice. So it's treating the ice as individual floating lumps really, rather than something with stresses in. And that's quite valid in the summer where the ice tends to move more freely, but it's less valid in the winter where the ice can be more compacted. And the motivation behind this is in the summer period, sea ice tracking from passive microwave satellite data is not so reliable because the surface can be melting, and it can be melting and refreezing as well in cycles, which can cause quite big differences between successive satellite images, which is not great when you're trying to match up the features in them. And increased water vapor in the atmosphere can also blur the images. So this is a work in a testing phase using a free drift model that was programmed by Javier Mozo in his master's thesis. And we're using ERA 5 wind speed data from C3S ECMWF, and we're using the OSISAT low resolution passive microwave ice drift product, which I showed earlier with the purple and the black vectors. So this is done by taking a historical training data set of ice drift data and wind speed data. And per month, we solve the inverse problem to find the parameters that link the wind speed to the sea ice drift. And these are the parameter files for June. So there's the Nansen number, which is some coefficient which links air and water densities and drag coefficients. Then there's the angle between the ice drift and the wind. And then there's the two components of the geostrophic water velocity. And these parameter maps are extended and smoothed so that they can be useful for all regions that there might be ice. When we create these parameter files, we get residuals and maps of residuals, and these tell us something about the quality. So these are simply the two components of the residuals, X and Y. The top two images are for June and the second two images are for December. So you can see that for the June residuals, they're actually relatively uniform. The June images are quite uniform compared to the December images, which show higher residuals and less uniform. So that's telling us that this method is going to be much more helpful in the summer. So when we have the parameter files, we simply can take the wind speed and use these parameters to calculate the ice drift. So for each daily map, we take the parameter file from the two bracketing months, calculate two different maps, and we use linear interpolation to end up with one final map. So here are some early results from late May, early June. And so far we've done this for the Northern Hemisphere only, so we'll be doing this for the Southern Hemisphere. And our next step is to validate this against the buoy data and see if we can refine it and investigate where it will be useful to use in the summer season, whether it can be used for patching or for supplementary ice drift maps in the summer.
2 minutes left.
Yeah, I'm on the summary slide. So in summary, it's been found that using swath-to-swath mapping for with passive microwave data is actually extremely good for making maps of ice drift. It's going to need good geolocation, and there's an interesting possibility to use wind speed data to calculate ice drift in the summer. And yes, if there's any questions, then I can take them and chat to. Thank you very much.
Okay, so the motivation behind this this work really is, as glaciologists, we're interested in understanding ice dynamic processes, including interactions with the ocean, calving, surging, mass balance, as others have mentioned already this week. And most of that stuff requires high spatial resolution and high temporal resolution. It requires acquisitions throughout the year because of the different seasonal effects, and some interannual reproducibility because of things like surges go on over many, many years. So what I'm presenting here is how Sentinel-1 has really addressed this gap in our observations since 2014. And I'm filling in a little bit of data here with some TerraSAR-X data that we got for the period just before. Now, I'm sure you'll start to notice some of the similarities with Lucas's talk from yesterday. And in a sense, I'm going to be presenting very similar data, but there are some differences, and I'll try and draw those out. I really like Lucas's talk. He talked about, for his dynamics work, quite a lot of places in the Arctic. I'm only going to be dealing with Svalbard. So for those of you who don't know anything about Sentinel-1 SAR, then this is a twin satellite mission launched in 2014 and 1B in 2016. Spatial resolution of the interferometric wide mode is about 10 meters. And in the later periods from 2016, we give a repeat period of 6 days. And this is fantastic for what we need to do, because it means we can use the images every 6 days, and we can also produce velocity maps every 6 days as well. And that really fills this gap that glaciologists really need to understand. And we have something like a 6-year consistent time series of these data. And there's a focus on the cryosphere. If you look at the coverage, this nice map from ESA showing the number of images between 2014, the launch of Sentinel-1 A, and 2020. And we can see an obvious focus of data acquisitions here over the Arctic and over Europe. And Svalbard is right in that sweet spot. So we're in a very good place at Svalbard to get these data. I calculated between 2014 and 2020, 862 interferometric wide full coverages of Svalbard to give us velocity maps, that number of velocity maps over that time period, which is really going to be extremely useful to us. Now, if you haven't any experience with the feature tracking method, this just illustrates it very nicely. We have an image here. This one happens to be from TerraSAR-X. And I'm going to move on to an image 11 days later, and I'm just going to step backwards and forwards between those. And you see those features moving. It's quite easy to design an algorithm that can then retrieve that motion, just like Emily was talking about, but on a much finer scale here over glaciers. So this is a single velocity map for Kronebrain in northwest Svalbard, showing you how good this is and how much information we can get from this. Now, TerraSAR-X, it has a spatial resolution of 2 meters. Sentinel-1, it's about 10 meters. And we can see the image quality is not as good, but we can also see that the quality of velocity map is pretty good. And so we can retrieve quite a lot of information from here. This is certainly good enough for most glaciological applications, looking at surging, looking at carving, and looking at mass balance. So the next slide here is a time series of these velocity maps from this same glacier. I'm aware that over Zoom, these animations don't always work so well, but I'm hoping what you can see is quite a lot of variability through the years. Here, the data is in the bottom left-hand corner of the velocities of Kronebrain, but also where my pointer is there, I hope you can see the movement backwards and forwards of the ice front, and that's another big diagnostic of what's happening in these glaciers, whether they're surging, what's happening in the carving, how much carving losses there is. So it shows us very nicely that Sentinel-1 gives us the velocity component of carving, but also gives us this ice front change. We had a very nice presentation earlier on today about ice front change and how important it is to measure that. So the opportunities provided by Sentinel-1 SAR then are really here, and we've seen them in the previous animation. We have images every 6 days. At a good spatial resolution, 10 meters is enough to really understand these carving processes. So we can get time series of glacier ice front positions every 6 days, and we can look at retreat, surge, advance, and carving using that. Unfortunately, we can't do that automatically. That has to be done with painstaking mouse clicks. I'll show you some of that data later on. We can also look at micro backscatter and look at the onset of melt and duration, but I'm not going to talk about that today. These time series also give us feature tracking every 6 days. And this is the departure between what I've done and what Lucas presented yesterday from Peter and his colleagues. I think I can get 100-meter resolution out of this. So I'm getting slightly higher resolution of the velocity maps. And looking at the paper that he circulated yesterday, there are some differences in the algorithms used and the parameters used in my feature tracking and theirs. And I think that explains some of the differences in some of the results we're getting. So these velocity maps then can allow us to look at time series of glacier speed at high resolution once every 6 days is very good, particularly now we have a multi-year archive. And we can also look at Svalbard-wide velocity maps, as Lucas showed, but I'm going to try and show you towards the end some of the interannual differences in velocity in Svalbard. So let's start off then by looking at some of the time series from individual glaciers, just taking a point on the glacier somewhere where you get a consistent time record. And I've picked out 10 glaciers here that have surged during the Sentinel period. We can see the surges in the increase in speed and then coming back down to normal quiescence. We had a short surge here for Arctic Brain early on, which actually required TerraSAR-X data prepended to the Sentinel data here. Morsnet Brain, also a fairly short surge, and is now reducing back down to its normal quiescent speeds. We've got a short surge in Osborne Brain, which is then picked up again in the end of last year. We've got long surges. We've got surges, for instance, Recherche Brain in the south of Spitsbergen that went up here nicely and returned down to a normal level, and then it picked up again. So there's lots of very interesting activity in the surge activity in Svalbard. We've got surges that have been going on all the time throughout the sequence here, and this is really just an ongoing surge. It's been going, as I think somebody said, since 2012. We have Negru Brain. Negru Brain is the surge that Hiroyuki on Tuesday, he was asking about some anomalous features in his images, and that he was looking at Negru Brain there. So that surge explains things. We also see here very nicely that even when a glacier is surging and it's really behaving according to its internal dynamics, it can still respond very clearly to the injection of meltwater and rain in the summer months. So it's nice to see that in almost all of these surges, but I think it's also very instructive to see that there are some surges, like in Songkhla Brain here and Kaval Brain, but we don't see that at all. So there's lots of interesting activity here that we can dig into, trying to understand these processes in a better way. Now, it's all very well looking at ice front positions and just plots of glacier speed, but actually Sentinel-1 gives us this amazing laboratory for really observing these glaciers and making time lapses of them, because it gives you a much better feel for really what's going on here. And this is Morsner Brain that surged between about 2015 2019, and we can see you can make a nice animation here, which is very useful for understanding the surge and for outreach and for education purposes. I know, again, this is not the best thing to put over Zoom, but if you just search my name on WordPress, you can find a copy of this if you want to put that later. And I don't know whether the resolution of your screen is good enough, but hopefully you can see the Eiffel Tower here, which nicely gives a sense of scale for this particular surge. So some other things have cropped up during this, this analysis of what's going on in Svalbard. I've looked at a lot of different glaciers. I've picked up on a lot of surges, as Jack Curler will tell you. I've spotted them first by always being on top of those data and processing each data cycle. Here's a couple of glaciers, Hinlopen Brain and Stone Brain, one in the northwest up here, and one in the southeast on Balansoya. And we can see how these are behaving very much like surges. We have a sharp increase in velocity and then a gradual decrease in velocity just in time to reach some kind of pseudo quiescence just in time for the next summer season to start. So I'm almost calling these annual surges. They're very interesting behavior. I think it's quite exciting that we're seeing this on more than one glacier. And this sits somewhere between the glaciers that simply trundle along and respond to the summer months, the meltwater input and the rain, and those surges, which are working over much longer timescales. This seems to fit somewhere in the middle of there. Now, Uta yesterday afternoon raised the question about sensitivity of these kind of data to what sort of losses we can get. Now, in an individual velocity map, as Peter in his paper actually tells us, the normal velocity sensitivity is about 0.1, 0.2 meters per day. And that's fine for looking at these surges and looking at what's going on, understanding calving processes, and even measuring those calving losses. But actually combining velocity maps, and I've tried a variety of techniques, monthly, these are quarterly velocity maps here I'm showing you here, to try and understand some of the activity, the dynamics that's changing on a much more sensitive scale. And hark back to what Jack was telling us about on Tuesday. He was talking about Kongsvegen and the surge of Kongsvegen that really is only just starting, even though he detected it in the GPS in 2012. Really, we're only just being able to see that now in Sentinel-1. And you see the scale here. This is exactly the same scale as Jack would tell you to expect to see velocities, but we're seeing velocities at 0.1 meters per day, which is, you know, twice the sensitivity as we'd normally expect for Sentinel-1. And that's simply because you're combining data over a full 4 months here, and that's a roughly 50 velocity maps. So the density of coverage over Svalbard gives this amazing opportunity to pick up these things that are very sensitive here. And that's exactly where we'd expect the surge to be, and we're only seeing it really by combining data, which requires that you have a very carefully designed method of filtering the data so that you can put everything together in a way that rejects the noise, but brings in all of this information from all of the data, all of the velocity maps. In fact, looking at Kongsvegen here also made me notice this hammer brain surge here. I haven't seen it before, but because I was working with Jack, I picked up on this one here. that seems to be surging in Hammerbrain and seems to already be responding in the calving front of the glacier, probably to meltwater flowing down beneath that glacier. We've seen that elsewhere as well. So we have amazing sensitivity here by combining velocity maps. I mentioned calving at the beginning, and this is a time series that allows us to combine both the speed here. This is the surge of Tuna Brain from TerraSAR-X in the beginning and Sentinel-1 towards the end, the full surge cycle here going on. This is the nearest station data from precipitation air temperature. And we can also see that I've digitized the ice front of this glacier 60 times a year ever since this satellite went up, which is a lot of work, but if you break it down into weekly tasks, it's quite easy. And you can see how smoothly varying this ice front data is, but that allows us to differentiate that ice front change to a rate of retreat in the pink here. So this is the retreat rate, and by combining the retreat rate with the speed, that allows us to actually quantify the rate of calving, the rate at which ice is being lost into the fjord. And we're doing that for a few glaciers around Svalbard. Okay, now I'm going to move on to some of these Svalbard-wide velocity maps, because I think these are things of beauty in their own right.
2 more minutes, Adrian.
Okay, thank you. In 2016, we had only 55 velocity maps. 2017, we were at 118 because of Sentinel-2, Sentinel-1B. Let's have a look at the changes that are happening here, 2018, 19, and 20. And what you can see really, the differences are mostly the surges going on. And these are the surges we've talked about. Tuna Brain over here, which has finished its surge in 2020. Here's Negri Brain and some of the others I've talked about. But interestingly, we can see differences here between ascending data, and ESA very kindly started acquiring descending data as well. So the backscatter you see is from a different look angle, but I hope you see that the velocities are consistent between those time series. And you can combine these together to provide a velocity map with 244 sources in a single year. And this shows us an amazing sensitivity to a slight rekindling of the Natos Brain surge right at the front, and something going on in Dr. Brain here, surge starting higher up. Let me finish off then by talking about the velocity change between these maps. Here's 2016 to 2017. Mostly what you're seeing in this plus or minus ½ meter per day is these surges. We've seen them before. But we can ramp up the sensitivity to plus or minus 5 centimeters a day because there are so many velocity maps going in. And we start to see more of a pattern, if you ignore the surges, of general speed up. 2017 to 18 is very much the same. And there are some of the surges here starting to see slow down, some of them starting up here, Monica Brain, Negra Brain slowing down, Tuna Brain slowing down over here. 2018 to 19, very similar. Tuna Brain is now finished its surge, so it's going on to the black colors here, whereas we've got Recherche Brain, Monica Brain still in full surge. But I think the most fascinating, we've seen mostly year-on-year increases in velocity, probably in response to warming, more availability of meltwater. But in the most recent difference map, 2019 to 2020, what we're seeing is a widespread deceleration. Obviously, a lot of these are ends of surges, but there are some places I draw attention to up in Vestfold up here, where all the glaciers seem to be slowing down in a year when actually it was wetter and warmer than we would have expected. I'll finish there with a conclusion. This is quite short. We love Sentinel-1, and I will very happily, just like Lucas said with his data set, share data with you. It's at 100 meter spatial resolution rather than 200. I don't have a great interface that you can just download it, but please send me an email if you'd like to have access to some of these data. Thank you very much.
Thank you very much. And thank you very much for the opportunity to present here today. I'm speaking on behalf of a couple of my colleagues here. My name is Marcus. Involved in this research is also Rolf Ohle. He is the one that developed the ultra-wideband radar that I'm going to talk about mostly. Eirik Malnes and Hanna Vickers, these are remote snow scientists, remote sensing snow scientists, with Eirik being the project leader. And Ture Riese, he is a pilot. The research that I'm presenting is part of two SIOS infrastructure projects. So our goal with these projects is to validate TerraSAR-X products and see if they can be used to retrieve snow depth and snow water equivalent over entire Svalbard. So we collected quite a lot of TerraSAR-X data over the last couple of years for Svalbard. The things that I'm presenting now is the validation campaigns for those TerraSAR-X products, or for the retrieval of snow depth and snow water equivalents. And there's obviously a couple of different ways how to do that. And we could, for example, use a normal GPR and drag it along with a snowmobile, or do field point measurements. But since we have also other projects that involve the development of a radar and a drone in combination, we chose to use this technology and develop this technology further to do the validation campaigns for the TerraSAR-X products. So in this April, we had our third campaign. We couldn't do a campaign last year because of COVID. And we chose to focus on a wider area around Longyearbyen, simply because it makes logistics a lot easier and safer. And we could do day trips out to our field sites. And the majority of these field sites we have now sampled for the third time now, and we'll do so one more time next year. So it's not only getting snow depth and density and so on from different locations, but do that also repeatedly. Showing a short video of the drone and the radar. So you see here the drone coming into the picture, and in the middle of the image, that's the pilot monitoring the drone. In the next couple of slides, I show you also the radar and the antennas, but you can see the antennas hanging below the drone. So here's the technical setup. The drone is a multi-rotor drone. It's a Fox. You can buy it off the shelf, but this one is then heavily customized for our purposes. It's a quite powerful drone that has 4 engines, and we can put a payload of maximum 25 kilos underneath it. It needs a lot of batteries, and we have several battery packs that we then also travel with and have out in the field. But I would say that batteries are the biggest constraint in terms of mobility. You can't put them on a plane, obviously, so you would always have to ship them or drive them to a location where you want to fly. The flight time was around 25 minutes. Now, if we had sunny and calm conditions in -15 like this, the flight time would always be dependent on wind speed and air temperature, but also at the elevation you fly and the ground speed you are flying. The drone has a GPS and a laser to hold position and elevation above ground. And we have our own autopilot that controls and navigates the drone. So you can preload any flight plans and tracks, and then the drone will execute them. The radar is that gray little box that sits underneath the drone. It's an ultra-wideband radar, so we have a bandwidth of 0.7 to 4.5 gigahertz with a ground resolution of 5 centimeter in range, 52 hertz measurement rate, so you can fly the drone quite fast, and we have flown it up to 10 to 15 meters per second without any problems in terms of the measurements. And it weighs 3 kilo. And then underneath those 2 green things, those are the antennas, with one sending out the radar wave and the other one receiving. Those are dual Vivaldi antennas, and they have a 3-meter field of view when you fly 10 meters above the ground. So that's kind of your footprint that you have. This instrumentation is a scientific tool. So we had a couple of design parameters for those that I wanted to mention. For the drone, it's autonomous flying. So we have a pilot that starts the drone, but then basically just monitors while it is flying and makes sure that everything works out, but then can always switch to manual if there is some problems. There's a lot of redundant power because the radar and the antennas are quite valuable to us. So if one engine, for example, fails, we still want to be able to fly the drone and land it safely. And it's very tightly integrated with the UVB radar. It means that the radar uses parameters from the drone and vice versa. The radar is very low weight. It has a radio link, so you can look at the radar lines in real time and see if everything works well. And it operates at low temperatures without any problems. And the antennas are low weight with a small physical footprint. They are highly directive, and they have the ultra-wideband characteristics. You can also tilt those antennas, so if you would fly, for example, up a slope, you would still have good directivity. So here are some impressions of the field campaign from this year. The setup would be that we would go to a location, then set up our tent and prepare the drone and the radar and everything. The pilot would always be outside and monitor the drone, as I said. And then in the tent, we would have 2 monitors with one have all the telemetry data from the drone that would be monitored, and the other monitor would look at the radar data as it is being collected. So one of the goals for this year's campaign was also to look at different flight or service scenarios that we could use, either flying in a zigzag or flying in a transect, to try to kind of survey the most representative and largest area. What we came up with in the end was an hourglass where we would set up camp in the middle of the hourglass. The size of the hourglass could be maximum of 1 kilometer. And then the drone would fly that hourglass. And to validate those drone snow depth measurements, we would also do a full snow pit with collecting different parameters. We would collect snow depth and their GPS locations in one of the sides of that hourglass, trying to match with where the drone would be flying and surveying. And we had also a couple of different locations where we just measured also then bulk density, which is an important parameter also to tune the radar measurements for snow depth. Just quickly in terms of how the measurements work is that the radar sends out the radar signals, and then you would have different reflectors, typically from the snow surface, the snow air surface, but then also from more prominent layers in the snowpack, and then from the snow and ground interface. So typical radar line would look like this then now, where you see the interface between the air and the snow, and then also between the snow and the ground, with a quite nice match between radar snow depth and in situ snow depth measurements, and also some of the more prominent stratigraphy in the snow ice layers, for example. And we could then also look at in situ measurements of the density of the snow, the hardness, and compare it to the mean backscatter from the radar. Due to its ultra-wideband characteristics, the radar is also capable of, for example, imaging fresh water over lake ice. So you see here in that radar plot an air-snow interface, and then an interface between snow and ice, and then a third interface between the ice and the water. So it was kind of water over the lake ice that we could also imagine, and then the signal would disappear once you go into the water. The same wouldn't work for sea ice, obviously. The tool is now, the radar is now very well validated. So we have been doing all those campaigns now, always done in situ snow depth measurements and compare them to those radar snow depth measurements and get pretty much high correlation. So we are very satisfied now with how the radar works, especially when flying it with a drone. For SIOS users, we generate different products that we are uploading onto the repository. Those are snow depth maps. As you can see here, we show here a comparison between in situ snow depth measurements and the UVB radar with a very high spatial correlation. We can also supply radar lines or simple tables with snow depth and coordinates. And at some point, and as I said, it is the goal of our SIOS contributions, is snow water equivalent and snow depth maps for entire Svalbard using the TerraSAR-X data. Future plans and the next step in terms of the airborne radar. We are trying to employ it next year also on a fixed wing drone, which means that we could fly even longer transects with higher airspeed. And we are working on a software-defined radar as well, where you could, for example, shut out different frequencies and get rid of problems with interference, for example. We've won more field campaigns, as I mentioned earlier, next year. And in terms of our SIOS deliverables, we have started looking into the TerraSAR-X datasets, but we are expecting to have our first results now ready this year. And with that, thank you very much for your attention.
Hi and welcome. The title of my talk today is Evaluation of Iceberg Detection Limits from Remote Sensing Data and Investigation around Negative Rain. My name is Laust. I'm a PhD student at the Arctic University of Norway in Tromsø. My research focus is on iceberg detection in the Barents Sea. At the moment, I'm doing fieldwork in the Arctic, so I'm not able to be here live with you today. Instead, I'm only showing you this recording. My colleague, Thomas Kramer, also from the Arctic University of Norway, should be able to, if all goes according to plan, to answer your questions after my presentation here today. I'll start with some background. The number of ships traversing the high north are expected to increase. At the same time, the sea routes are expected to open up as the sea ice extent is reduced in the future. A warmer climate and the need for new resources are driving economic investments all over the Arctic, and all this are putting more ships and infrastructure in areas with icebergs and the risk of icebergs. Yet there is a serious lack of sufficiently accurate methods for estimating the number of icebergs and their location and movement. Within remote sensing, we typically distinguish between optical and radar images. As most of you know, a synthetic aperture radar called SAR is well suited for Arctic applications, as they're able to see through clouds and acquire images regardless of light conditions, which is good in the Arctic. Through the Copernicus, the European Copernicus program, we can get daily coverage of the Arctic year-round from the Sentinel-1 satellites. Just showing you a quick example here where we see that Sentinel-1 is able to see through the clouds and capture what is underneath on the water surface, as opposed to Sentinel-2, which are only able to capture images in cloud-free conditions. In order to detect icebergs in open water, the backscatter, that is the signal that is scattered back towards the satellite, must be distinguishable from that of open water. In most cases, that is true. Icebergs appear to have a higher backscatter in water, and that the problem of detecting icebergs can be solved by detecting bright outliers in sea clutter. The simplest way to detect these outliers are using a constant false alarm rate filter. Here, I just show a short example in the bottom left corner. We apply a filter that runs over the image, and for each pixel we compare that pixel against a local neighborhood in the gray area here. If we, for example, assume that the sea clutter is normally distributed, then we could calculate the mean and standard deviation of the background and then set a certain threshold area and say, okay, if the center pixel is above this value, we would assume that it's an outlier. In that sense, a SAR filter is automatically adapting to the local conditions. This method works great in open water, as we see in the examples here. In the bottom right corner, we see the detections made in the top right image marked as red. We also have some detections on land, of course, but those can later be removed in post-processing. In our project here, we have focused on a small area near Negri in Svalbard. This area is very dynamic with a lot of icebergs. So in order to verify the observations we're doing from Sentinel-1, we are using optical Sentinel-2 images. Unfortunately, the satellite overpass between the two satellites have a time difference of up to several hours, and they can't be compared one-to-one when the icebergs are moving. Therefore, we have focused exclusively on grounded icebergs, that is, icebergs that remain stationary for a period of time. Those have been detected or identified by making a time series composite of Sentinel-2 images, as shown here in the bottom, where we apply a minimum reducer in Google Earth Engine in order to detect objects that are not moving. Using this method, we have detected 45 grounded icebergs in our small AOI. The smallest have a pixel area of 4 pixels and the largest of 288. That is in 10-meter resolution images. Then we compared these detections against 9 Sentinel-1 images, 7 of which were of the extra wide swath format, 2 were of the interferometric wide swath, and we applied a SAR filter on these Sentinel-1 images. Our SAR filter was based on the complex Wishart distribution, which accounts for both bands in Sentinel-1. As most of you know, Sentinel-1 is dual band, and the simple method I showed on the previous slide only uses one band, but we're using both of them. The Sentinel-1 detections was applied on the entire time series of 9 images, meaning that we have a total of 45 icebergs times 9 images is about 400 objects, which were then used to calculate how often icebergs of different sizes have been detected. As we see in this example, the minimum composite on the left shows the stationary icebergs in white compared against the number of times an iceberg was detected in the extra wide swath and interferometric wide swath data respectively. We see that the stationary icebergs are, as expected, detected several times. We also have a lot of detections happening only once, which is likely icebergs or sea ice moving around in the individual images. Some icebergs have been detected multiple times in Sentinel-1 images, but are not visible in the composite on the left. And some of those were icebergs that were stationary for a shorter period of time, several days, but not for the entire period of time. We have split the results according to the iceberg size using the WMO definitions. The iceberg size in our case was calculated as the square root of the pixel area. For extra wide swath, only about a third of the medium icebergs was detected. These are icebergs that are well above the pixel spacing, the resolution, which we expected to be able to detect, but this could be attributed to the dynamic environment with a lot of icebergs contaminating the SAR approach. For interferometric wide swath, almost all of the medium icebergs was detected and all of the large icebergs was detected. Just to recap, the interferometric wide swath have a pixel spacing of 10 meters and the extra wide swath have a pixel spacing of 40 meters. Normally, the extra wide swath images are processed and delivered from Copernicus in a ground range detection format, which have a pixel spacing of 40 meters, even though the actual resolution of the images is about 6 times 20 meters. Here we have tried to compare the original GRDM image in the bottom left corner against a SLC singular complex image that we have processed to 10 times 10 meter resolution in the bottom right in order to visualize what we might miss in the Copernicus processing level. Grounded icebergs are clearly visible in the bottom left image as in the bottom right image. In the bottom right image we have a higher noise level, but the icebergs are still visible. Also, it appears as if the delineation and size of the icebergs should be easier to detect in the bottom right image, as well as if we have icebergs close together, it should be able to detect them as individual icebergs in the high resolution compared to just single smeared together objects in the bottom left image. Of course, the interferometric wide swath image is much better than both of them. It has a better resolution, but as the extra wide swath image is the most common format used in the Arctic, we need to consider using these images. The single complex image processing will of course increase the computational requirements and storage requirements, but we might be able to use simpler detection algorithms on this image format and also perform better detections here. So this is something that we would like to look further into in the future. Then on to some comments and future work. At the moment, the CFAR approach is the most common way to perform object detection at sea. However, CFAR filters have previously been shown to operate well in heterogeneous areas like the one showed here in the right image or the one we have just looked at. A high density of icebergs might lead to missed detections or false detections, which could explain the low detection rate we had in the study. In the future, we'd like to investigate the relationship between icebergs detection rates in thin-loop complex and ground-range detected images more thoroughly in order to figure out which format is most suitable for iceberg detection. We also need to investigate how to properly handle heterogeneous areas with a lot of icebergs, maybe using alternative methods such as segmentation. For the extra wide swath images, we need to consider the varying incidence angle and noise levels as seen in the rightmost image here, which might affect the detection accuracy. And then we need to calculate the effective false alarm rate, how many icebergs are missed and how many false detections do we have. This is not something that we really properly considered in this study. Additionally, can we do anything about the smaller objects such as growlers, which also pose a danger to marine traffic? And is it possible for us to determine the minimum size of detectable icebergs? Some of these issues can be addressed using high resolution images. We have here in the bottom right shown a Dornier flight image, a high resolution optical image from our study area, which can be used to answer some of the questions above. These images can also help us identify which objects are sea ice and which are icebergs. Yeah, that was all I had for today. Thank you all for listening in to this recording. I'll be looking forward to hear some of your questions later and also seeing some of the other presentations when I get back to Tromsø. If all goes according to plan, my colleague Thomas Kramer should now be ready to answer your questions.
So thanks for having me. I'll talk today about search-related changes in Nikribri and Svalbard observed with ISA2, two components which are intrinsic to the Svalbard Remote Sensing Conference. The talk's co-authored by Tom Trano, Matt Lawson, and Adam Hayes. And I don't even need to say where we are because Sridhar did this for us. So thanks very much. This is what our group is all about. Fast-moving glaciers. This is, of course, Nikribri during search in 2017. Airborne field campaign and mathematical algorithms for analysis of remote sensing data. And a notable thing about any math we make is we look first at the science and whether there's an open problem. And then if we cannot solve the problem with existing techniques, then we'll make a new mathematical algorithm, such as the density dimension algorithm for ISA2 data surface height retrieval, which I'll talk about later in this talk. Okay, so we'll look at the following topics. Of course, the search of Nikribri, about which you've already heard in various other talks. The DDA ICE, which is the surface height retrieval algorithm for ISA2 data, and ISA2 airborne validation campaigns over Nikribri, which were co-funded by SIOS in 2018. So thanks for that again. And then we take a look at higher level ISA2 products, roughness and crevasses under snow. And lastly, actual changes in Nikribri during search. The work presented here is supported by NASA Earth Sciences, the Nikribri search by NSF, National Science Foundation of the United States of America, Arctic Natural Sciences, and then we have some cyber infrastructure projects and so forth. The project is registered as Research in Svalbard Nikribri search. And we had a SIOS Access project. Of course, I would like to thank everyone at SIOS, NPI, UNIS, Airlift, and the captain crew of RV Lanze, without whom any of this work would not have been possible, especially the field work part of it. I also thank the science team for ISAT2, UNAFCO Boulder, and Planet for SkySat data collection, and Paul Morin, who speaks after me, for collaboration, and some more team members. Okay, so I think everyone knows all this. Glacial acceleration is the largest source of uncertainty in sea level rise assessments, simply because it's lacking inclusion in the worldwide models used to create such assessments. However, something like Negri during 3 months of the initial part of the search equals about 1% of global annual sea level rise equivalent. So that is a lot. And so if you look at the search glacier here, right? Oh, I don't have the slide twice. If you look at the search glacier here, you see the surface is really rough where the ice is moving fast, and we have spatial surface changes in height over really short distances. And so that actually motivated the use of an advanced topographic laser altimeter system on NASA's ISAT2 as opposed to the pulse limited types of systems that were used during the ISAT class data collection. Now to the glaciological motivation. We take an approach centered on surface roughness and crevasses as indicators of glacial acceleration, which is exemplified here by different prototypes of fast movement, such as the Bering Glacier in Alaska, which surged in 11 to 2013. Here's, of course, Negri and Jakobshavn's Isbre, which is always moving fast and the best studied outlet glacier in the Greenland ice sheet. Now, if you zoom in on matters a little bit, you can see in these images, these are Planet SkySats, you can see that the surface morphology generated by the crevasse field actually is totally different, and that we draw information on the dynamics of the glaciers from the type of crevasses we see. So then next, so this is Jakobshavn, this is Negri. The line here is an ISA2 crossover, and you can see that with the algorithm to be talked about later, we are able to retrieve totally different crevasse morphologies in surface height profiles. So you see Jakobshavn has all these shoulders in the crevasses, which you see in the imagery, while Negri just surges, so the crevasses open once and then they pretty much stay. Okay, here you can now see why we take the roughness-centered approach. You learn in school that everything is differentiable, and if you take calculus 2, it still is, but it's not. The world is really rough and in more than one sense. And you can see this sort of manifested in the imagery taken here during the start of the search. What's notable is that the crevasse provinces actually show similar patterns over spatially connected regions, so we use that in statistical analysis. Here are some more images to enjoy, just so you see the patterns are really different. Now, not only is this of glaciological relevance, the glacier during search also presents an ideal test situation for evaluation of height determination over crevasse and other complex surfaces, simply because you don't have to fly so far to sample more than one surface type. Okay, and here notably, like Ottlandsbreen is not surging, but Negri is, so you clearly see a boundary between the roughness provinces. We have made Negri velocity maps from Sentinel-1 using the snap toolbox, which of course pales in comparison to stuff Adrian does. However, you can see how the search expands going from 2017. This is not the fastest map, it was 22 meters in July, like just sort of a couple of days before that. Well, a couple Sentinel sets before that. And then this is 2018 in the next map, then 2019. And so you can see an overall slowdown in the velocity, but we have the highest velocities always in about July. Here are maps from 2021. So this glacier search is still going strong. A typical length of search is on the order of 7 to 10 years. We'll still have to find this because the last search was in 1935-36, so there is no study using modern observation techniques. The top ones are just linear scaled maps. The bottom ones are logarithmic scaled maps, which sort of map out the area that's now affected by the surge in better, it's sort of just easier to see, right? So we can see that while the surge gets slower, it does expand further up the glacier. Okay, I threw this one in for Paul. So we are also doing a classification based on worldview data, which we have a connectionist geostatistical classification system, which allows to identify 13 different types of crevasses in the glacier. We have a time series of these, but the talk's supposed to be on ISAT2. So, all right, now.
1,387 different orbit paths every 91 days by ISAT-2. The orbit pattern creates a dense grid over the poles, all anchored here at the Greenland Summit Observatory. Since each orbital path will repeat every 3 months, scientists will be able to observe ice changing between seasons. The more frequent measurements of the polar regions will give us a more detailed look at retreating glaciers, melting ice sheets, and thinning sea ice, and the global impacts of those changes. .2 microradians, that's the angle of pointing stability of the Atlas laser. If you placed a silver dollar 28 miles away from Atlas, the laser's center would stay on the coin. That kind of stability is absolutely critical for the spacecraft to measure the height of Earth from orbit. To ensure pointing stability, Atlas uses the beam steering mechanism, which is a motorized mirror that moves to compensate for thermal changes that happen in orbit and prevents the Atlas beams from bending as they head for Earth.
So remember this, please. Okay, letting others do the work for me. So now back to my talk. Were you all able to see the little movies? What's this here? Sharing screen. So yeah, I thought the movies were better than all this. ISAT was launched in 2018. So can you hear me back again? Someone should give a thumbs up or so, like the convener or someone who has video. Thanks. Okay, I wasn't quite sure about the transmission of these YouTubes. Okay, so now, as you saw in the movies, there is a new technology involved in the photon counting laser altimeter, which was a discussion at the time when I was on the, so I'm a member of the science team for ISAT2. I was a member of the definition team in 2008, long time for any early career scientist. I know, 10 years, gee, I'm still gonna be in science even. So there was discussion, should we go with a pulse limited laser like ISAT had, or shall we go for this new micropulse photon counting technology, which actually records all the background photons so that's a lot of photons during, say, daytime, right? And then which photons are actually the signal photons from the active sensor. It is an active sensor, but it's kind of weird, so it's an ill-posed mathematical problem. And things like vanishing sea ice or fast-moving glaciers with high spatial variability led to the acceptance of the photon counting sensor. And back then I said, all right, I'll make an algorithm, we'll find the data. And so that's what the DDAIs actually is. Other people are making algorithms too, such as the land ice product. Okay, so here you see DDAIs. This is an example taken from Nicriprian, actually allows to follow along the top of the surface and into crevasses for the strong beam, as you saw in the movie, and there's also the weak beam always in the same pair. And we get surface height at sensor resolution, which is 70 centimeter long track from space, unless they're clouds. Okay, so a little bit of what DDA does. We look at the returned photon image. This is in the product ADL03. We kind of see these blips, these turn into the crevasses later. And then we calculate a density field using a Gaussian radial basis function. And the idea of this is we plot the information and then we automatically search for signal background separation. So we don't have to sit there and babysit the algorithm during daytime, nighttime, and changes in surface reflection. Then we identify the photons and we have a surface follower which automatically adapts to roughness. The algorithm automatically knows, like in the last panel here, when it's over smooth terrain, so then it adopts a different interpolator. Here is a bit of the mathematical characteristics of the algorithm. Notably, if you have been pulling ISA2 data off the internet, you likely have opted for ADL06, which is the Landis product that resolves surface height only in 40 meters, while ours has 70 centimeters, which is sensor resolution. That is afforded by the use of the radial basis function, which is some math taken from how you program a neural network, but it's not a neural network. That fact actually makes it really fast. Okay. Here's the fun part, namely the field validation campaign. We have in 2017 actually gone out to start to analyze the search of Negribrian for its own sake, and then combined this in 2018 and 19 with airborne evaluation of the ISA2 measurement capabilities, such as can we actually see crevasses, fractures, rifts, water and ice, firn, snow, and the like, along with evaluation of the DDA ice and 2 over crevasse terrain. We've also carried out some RTK GPS experiments together with UNAFCO to figure out how we best underfly tracks that have this really high accuracy while the helicopter weaves around in the wind, but we've done pretty good. And we had a special acquisition of Planet SkySat data as part of the NASA SmallSat data evaluation program. Tom Trano is a co-author. He took the photos. So that's Matt. Tom went on every field trip. That's Matt Lawson. That's Connor in the year before, setting up the GPS station. So we are collecting laser altimetry with a small profilometer integrated by our institute, time-lapse imagery, and then some correction data. Now, of course, the first campaign we did in 2018, the satellite was launched in the fall, eager to look at the data. Glaciers covered by snow, what do we do? But then we found out, hey, there are actually little blips under the surface. So we quickly flipped the algorithm and ran it several times over the surface, and we can see what looks like crevasses. So now we are actually for the first time able to see what the glacier is doing when it's covered by snow. We have validation data from the summer, but you can see the shapes and spacing of the crevasses are the same, which means what looks like crevasses is crevasses. Then we went back in 2019 when we were able to do a near-term validation of ISA2 flying tracks of within like a day of the actual ISA2 data acquisition. Here are surface heights from our laser altimeter instrument collected over Negribrian, of course. And now we want to know how good we are with underflying tracks. So this right image shows a SkySat with predicted ISA2 paths. So since you paid attention in this video, right, there are 1387 predicted paths. So we underfly one of these paths, but the pointing accuracy also means the paths, well, the paths are not exactly where they are. So they are like, they can be like 10 to 20 meters off. Distance from the helicopter to the path is a respectable 20 meters or so, considering in the end we had something like 30 knots wind, 60 kilometers per hour. That's actually quite good. Here we have corrected all the ULS data using the differential GPS correction and what's called the IMU correction. So for STRIDA, these are all the figures for a better version of last year's talk, which will go into your paper, into the paper for your journal real quick. We do look at crossover points to get an idea of the accuracy of our field validation data, which is in the order of 10 to 20 centimeters with something like a 2 to 2.5 meter standard deviation. Which means, yes, we can use them as evaluation for the ISA2 data. If we look at first this figure, the top shows us ISA2, the bottom shows us the ULS data. The shapes are not exactly the same because the ULS uses near infrared while ISA2 uses green. So the interaction, especially with slush and water and whatnot at the crevasse bottoms, is slightly different, but the spacing and depth is comparable. On the right, we have the first higher order product, which is surface roughness calculated from ISA2 and from ULS. It's no surprise that higher roughness coincides with crevasses, right? But now we can look at the ISA2 imagery, at the ISA2 results, calculate roughness for the entire Greenland ice sheet or for all of Svalbard, and we can see where crevassed regions are coming about without having to have imagery below it all the time. So here's another image evaluation of the data. These are GoPros of dry crevasses, the GoPros of water-filled crevasses, and the algorithm works regardless. Now, here is a look at how the algorithm actually performs compared to the current official algorithm released by NASA Goddard Space Flight Center. So the blue lines is ADL 06, that's the land ice product, which simply speaking just fails over any crevasse terrain. And of course, there's no second layer. So the little blue things are just the official product. It gets worse if you're looking at crevasses without snow actually. Okay, so this is from a paper that's coming out in print this month and online a few months ago. This is a bit of a complex picture. We compare easy situations, meaning nighttime data, night it's dark, right? So not so many photons in the background. And a case of simple crevassing, which is over Nigribreen, we have these square top blocky crevasses pretty much. The first level of the algorithm shows you the density field, right? So you have higher reflections at the surface, lower reflections at the bottom, and left is strong beam, right is weak beam. The official algorithm puts all the photons into 3 categories, which then in the end leads to failure of surface detection. So if you look at this, I hope you see the mouse. If you look at the surface retrieval at the bottom, the blue is what you get if you download ISA2 data off the internet, and the red is the DDA ice results. So we're working towards a research level product and hopefully an official product based on the DDA ice one. This shows Jakobshavn's Isbrae. This is for daytime data on complex crevasses, as initially discussed. Different glaciers have different surface types. And again, this is the photon classification. Here is the difference in surface height retrieval. Again, the blue little lines are wherever you get a blurb of ADL 06 surface estimation, and the red is the DDA ice surface estimate. Okay, so now we can of course make maps, say, of a year of ISA2 data. They are plotted in a way that you see where the tracks are. We can also make interpolated maps as we have done for all of Greenland. This gives you surface elevation here for the Nigribreen glacier system. What I find more interesting is actually the surface roughness, because now you can see overlaid on a Landsat image from the same, well, from 2019, from the summer. So it coincides with the 2019 data. You see the red areas are where all the crevasses form. We've been previously looking at this little crevasse field between Nick here on just in Upper Nigribreen. And now we can compare. This is a result we just got yesterday. We used all the data in the previous compilation to find tracks that are really closely aligned. This is a segment over Nigribreen located approximately here. And you can learn quite a few things from this image, because first, the crevasse shapes really don't change. So that's what we saw intuitively, say, with the geographer's eye before. A surge crevasse opens once and then it pretty much stays. The crevasses get a little shallower. So the top is the 2019 line and the bottom is the 2020 surface height over the same crevassed area. We did check the track separation is 20 meters upstream, so there's definitely a surface lowering, which must be a dynamic effect of an instability that builds prior to the surge collapsing at this time. So you can see it lowers by 12 meters, maybe a little more because of the offset. Why is this not just melting? Well, see, if you take the entire track across, now we include the area of the side glacier that's not surging, which is here, and the other side, which is also not surging, then you can see in the surface elevation comparison that we get about the same heights. So if it were just melt, right, it would melt here as well. It's just as warm and here. So you can see that that is an effect of the typical mass transfer, where the area in the upper glacier transfers mass to the lower glacier, so we think, from knowing previous surges. And here are some values to go along with this. The elevation change is about 11 to 12 meters along this segment. And the track separation works in our favor, so it's probably like 12, 12 and a half. The slope of the glacier is not that high. Right there. Here are, if you want to do this yourself, anything NASA does is open source, open science. You can grab ADL-03 data, which I've used in this talk for my analysis. On the Earth data side, the DDA ICE results will be developed into an ISAT-2 Atlas research product. I'm trying to push for a worldwide DDA ICE product, but so anyone who wants to work with us on this type of topic, we are currently taking an approach to use so-called early adopters who want us to check out their area, their data. Happy to do anything for the New Orleans glaciers, I've said to Jack a year ago or two even. And we plan to create a special product for all of Svalbard ice surface heights. Bunches of papers for people to read. Okay, so far so good. Are there questions?
I appreciate the invitation to come talk to you today. As Sridhar said, I'm director of the Polar Geospatial Center at the University of Minnesota, and we're a science support organization, primarily funded by the National Science Foundation, to provide geospatial support for NSF activity at both poles. And so, you know, in the most basic of descriptions, we make the maps for US investigators at both ends. And in Antarctica, for example, we have a seasonal office in McMurdo, and we provide, you know, real-time and near real-time support. In the Arctic, it's mostly remote. We've got about 24 people, it depends on how you count, you know, between staff and students and that kind of thing. And what I'm going to talk about today is the US effort for producing publicly available high resolution digital surface models, well, DEMs, you know, for the Arctic. I mean, you guys are interested in Svalbard, so we're going to talk a little bit about how all of this happened. And so one of the aspects of the Polar Geospatial Center is, because we are US government funded, we really don't receive any funding from the University of Minnesota. University of Minnesota is the host for us. I mean, there are all kinds of, you know, in-kind support, but our operations are US government funded. And because of that, we have access to imagery that's licensed for US government purposes. And in the case of what I'm going to talk about today, we've got access to Maxar imagery, what many of you may remember as either digital globe or GeoEye, high resolution optical imagery. And what happened was, about 12 years ago, we got access to this imagery, and we've been building the capability to transfer the imagery. We have been building the capability to process the imagery. This stuff is just incredibly fabulous imagery. I mean, we're talking really about, you know, 30 to 50 centimeter imagery from orbiting telescopes, and you know, unlike satellites like Sentinel or Landsat, these satellites are tasked. You have to, you know, give your opinion. You have to put in your request of what you want collected. And the downside of this is you don't have the repeatability that you have for Landsat, where you can expect over X number of days you're going to get, you know, these collections. The upside of this, though, is you can shape exactly how imagery is collected. So you can say, I want to look at this glacier, I want to look at that town, I want to look at this coastline, I want to look at these penguins or those polar bears. And it's extremely valuable. I mean, remember that this is basically a commercial, this is a commercial company that is licensing imagery largely for the defense and intelligence communities in the US. And so about, what would it be, about 6 years ago, the US was chair of the Arctic Council under the Obama administration. And as part of the effort, the National Geospatial Intelligence Agency and the Polar Geospatial Center proposed that we produce a high-resolution digital surface model of the Arctic and make it available. And we kind of knew how to do this. You know, we had software, we had some high-performance computing, we had imagery, but we never really had the resources to go into this to produce a product, you know, that in essence is about 10% of the surface area of the land surface of the planet. And so we put together about a 2-page white paper and circulated around NSF and NGA. It eventually ended up at the White House in the Office of Science and Technology Policy. And eventually it ended up being put forward to, and you know, as a project. And so let me go to the first slide and let me make sure I can get the, okay.
To make your plans a reality. And to help Alaskans better plan for sustainable development, the National Geospatial Intelligence Agency and the National Science Foundation are leading a public-private collaboration to create the first ever publicly available, high-resolution, satellite-based elevation map of Alaska by next year and the entire Arctic by the year after that, so that we know exactly what's taking place all across this great state.
So a couple of things about that. One is if you guys ever run kind of a large group, there's nothing to motivate a team like having the president announce your project. The second thing I just want to note is I show this to my kids every morning just to make sure that they're suitably impressed by my by what I do for a living. No one, you know, they're not, I can tell you that. But and so what this does though is this unlocks resources when something like this happens. And so, you know, just to kind of put all of this in perspective, this you know, in a way it's not the full constellation of Maxar satellites, but, you know, this is what we had available to us when we began the project. So primarily we were using WorldView 1, 2, and 3. Iconos was 1 meter and not that great for stereo. GeoEye, you know, it was okay back then, but it was still having problems. QuickBird was, you know, also an early satellite. So we were primarily using these satellites. And remember what these things are. They're telescopes pointed down. I mean, this is, you know, small versions of Hubble pointed the other way. And you could do some pretty amazing things with them. So the other thing we need, and we needed, which was software, and this was written by MJ No of of the Ohio State University, along with Ian Howitt, is that we needed photogrammetry software. And traditional photogrammetry software has somebody in there, clicking points. But the good thing about this imagery is what you can do is it is so well located. It's located to, within meters, depending on where and how you treat the imagery, that you can do photogrammetry unattended. So this is key. We're talking about millions and millions and millions of square kilometers and hundreds of terabytes of imagery. You don't have the possibility of even with students going in and picking points. The other thing you need, other than imagery and software, is you need computing. And the good thing about NSF is it's one of the primary places where the US government funds computing, and it's funded for research use. And so we got access to this computer called Blue Water. So this is a computer at the University of Illinois. It's still there. It's largely just for our use right now for continuing the work. But at that time, we were getting allocations on this computer. When it was built, it was about $200 million. It's 720,000 cores. This is a big machine. It's got a building built around it to keep it going. And, we never thought if we were going to do, Arctic elevation, that we could do it from open source software, that we could do it with basically defense and intelligence funded licensed commercial imagery. And, this big computing with, we've got, multi-hundred gigabit networking. And we never thought that that's what it was going to take to get the elevation done. And so you heard President Obama, the White House, the schedule wasn't driven by us. They said, year one, produce Alaska. It's like, well, there you go. I mean, this was, trust me, an experience to get this done. Software had to be written, procedures had to be put in place, workflows had to be developed. And in the end, we were able to produce, the largest of the US states. And, in the second year, we produced, in more than 90% of the Arctic at, originally the idea was to produce something like 10 meters, and eventually we produced, we produced a higher resolution elevation model. It's basically a meter. And so, just to put this into perspective, these are, this was a figure that was put together by some colleagues of ours in Iceland. The nice thing about Iceland is, for us, it was so small. So we do a lot of testing on Iceland. And so this is the Reykjavik area. This was the elevation model available for Reykjavik before us. And then we produced the elevation model, and that's what this is. And so, if any of you have looked at the Arctic Dem data, it's got its problems, but, it's some pretty amazing things. So here's some of the early data, for a crater in Alaska. This is the before, this is the after now. The USGS has flown some amazing IFSAR for Alaska, but, it's just amazing what we now have available to us just a few years later. Here's a place in Kotzebue, Alaska. We did this early on because that's where President Obama announced the project. So this was the elevation model before and after. I mean, it's good enough that you can see, the roads through the bogs. It really is something amazing. Here's Anchorage before and after. And if we zoom in, here's the Ted Stevens Airport for Anchorage, and those are airplanes. So, the elevation model is high resolution enough and good enough that we have the problem of how do you remove airplanes. Then, for us, this was just amazing. This is Point Hope, Alaska. So if you go, about halfway up, 2/3 of the way up in Alaska, and then go all the way west. This is a sandbar, and Point Hope is right there. It's good enough you can actually see the seawall, keep the town from being flooded by the lagoon here. And so, remember these these satellites are constantly orbiting, and we're trying to figure out exactly what we can do with it. And the primary thing in the first place was to produce a mosaic of the Arctic. But we quickly understood that we were able to go in and look at the Arctic through time. So this is something by Mike Willis of CU Boulder. And it's the Vavilov ice cap. So if you go to the middle of Russia and then go to the top right before you get to Canada, this is Vavilov. And what I want you to do is look on the left-hand side of the ice cap in the Kara Sea here. And then we're going to look at elevation models each year for a few years here. So this is March 2013, 2014, 2015, 2016. So this is a cold base glacier surging. It's not supposed to do that, but it's something that we were able to see here. And we kept going in and kept analyzing this. This is from Chun-Li Dai at the Ohio State University. She's moving to LSU this fall. She started to take this incredible stack of elevation models. She would use the rock as control. And then she started to look at what the change was. And you know what you're looking at here on this image on the right is not change in elevation, but depth of the DEM stack. And so you can see places like Peterman have upwards of 100 DEMs deep. You can look at the other outlet glaciers and you can see we've got an incredible wealth of data here. And she started to go in and look at the ice surface, the change in the ice surface elevation rate. And so on the left here, you'll see, that, we're going down by meters at a time. And on the right, you're looking at the uncertainty here. So the uncertainty that she's finding, basically a lot of the error is sub-half meter for most of the areas. It's just, as you go into the ice sheet, the error increases. And then you can start going into specific areas and you can see basically in meters per year, the change in the ice surface rate, basically on a meter by meter basis for the whole island. Ian Howitt's doing something similar, but instead of the rate, he's looking at overall structure from year to year. So Ian's making elevation mosaics on an annual basis for all of Greenland and then subtracting it. So this is 2020 subtracted 2019 subtracted from 2020, and you can go in on a 10 meters, grid cell basis and see exactly where things are changing. And you can see, where you have something green here, it's not changing, and it's not changing generally because that's the rock, that's the vegetation. It doesn't change all that much. And so we've got another release of Arctic DEM coming out the end of this year. It's going to be over 2 million timestamp DEMs, a new mosaic using a new technique where you stack all the DEMs and you kind of look for the median, easily 100% coverage of Svalbard. And, on the right there, you see a table of how many DEMs per year we have for Svalbard, and then also how many just in the Arctic together. You see we have near full coverage of Svalbard every year. And in fact, in some years like 2015, 16, and 17, we've got Svalbard multiple times per year. We're also kind of hedging our bets. We don't know exactly where commercial imagery is going. So there's a concept at NASA that we've been helping with called change. And this is a proposed instrument where you have a satellite that is specifically built for 1 meter elevation model. So you have one vertical telescope, and then you will have one forward-looking telescope. And also in the vertical telescope, you also put a LiDAR in it for ground control. And so one other thing I just want to talk about just before I end here, because I want to give you guys some time for questions, is we're using the imagery for other things. And so remember, what we have here is NSF supercomputing. We've got lots of imagery. We've got people developing open source software. And so this is, there's a team at Woodwell. It used to be a chunk of Woods Hole. or it is a chunk, but they're going under a different name right now, with Anna Liljedahl, who's working there on some permafrost issues. And what they've been doing is developing AI techniques for identifying structures, you know, that you see on the ground when permafrost or thermal karst starts to degrade. And so, you know, we all know these stories that chunks of Alaska are washing into the Arctic Ocean. We know this progression where you see ice wedge polygons, they melt, and then you start having, you know, this kind of permafrost thaw over time, and you can kind of see the landscape change. Well, the good thing about having time-dependent multispectral imagery at about 30 centimeter resolution for the whole Arctic is if you were to develop AI techniques, you'd be able to go in and identify these structures and watch them. And so here's a chunk of an image from Barrow, Alaska. And what we're looking at, this is, you know, imagery of the area. You can see the different polygons melting. And so what Anna's people did was they went in and they would have an image of ice wedge polygons. They would train an AI on what these polygons look like, and then they would detect it and segment these polygons out. And it really, really lends itself to some interesting analysis. So you can go and automate this whole thing. You can start identifying ice wedge polygons. You'd never be able to do this by hand and be able to go this. So, you know, what I want to point out here is not only can you identify the polygons, but you can do it repeatedly. And so instead of just counting polygons, you really can do a polygon census where you can look at the polygon, get the area, and then start watching it over time. And so you can go in and see polygon number 27 and see what happened. And then you start getting things like this, where, you know, the green in the image on the right are the individual ice wedge polygons that have been identified in the imagery. And then they also have trained an AI to identify infrastructure. And so you can go in and see all of the infrastructure and look at the intersection and see whether the ice wedge polygons are changing adjacent to the roads, for example. And so really this is where a lot of NSF and NASA and other agency investigators, what they're working on now is how can we monitor these small structures over time? How can we extract the science out of it? How can we identify the change? So, you know, once you have this kind of IT infrastructure, the high performance computing, the software, then you can train to look for different things. You can look for coastline, you can, you know, in the imagery, and then you can start using the AI to analyze all of this, because, you know, the days of being able to hold imagery on your laptop are over. I mean, we're producing elevation models, you know, in such volume that releases are in the hundreds of terabytes. So you're going to have to work on it in the cloud. You're going to have to work on it with HPC or something else. But with that, I just wanted to say thank you for the invitation to come talk to you, and I'd be happy to take any questions.